Okay. Hi, everyone, and welcome to the second day of the second training school of challenges. I just here to inform you that as like yesterday, we are recording also today our interventions and our presentations. Here you can see the agenda. Sorry. So today's agenda, we are starting right now. Sergey should connect online, but he's not here yet. So we will move Stefan presentation up on the metrological Raman spectroscopy. He will be the first one. And then we will have Yovav and Shira from Israel. And if Sergey connects, depends on whether he and when he will connect. We will have then a coffee break from 11. A 10-minute coffee break, probably will be more, depends on how quick we are. And then we will have some presentations on sustainable silicon photovoltaic cells, on process control, on metadata extractions, lunch, and we will end with the presentation of Vittorio from transmission electron microscopy, and a final presentation from Ennio Capria on the work of EMMC. So let's start with Stefan on metrological Raman spectroscopy for strain characterization. Thank you, Stefan. And let me just share. Stefan, this one. Okay.
So, good morning. So, my name is Stefan Mundrak. And I work for the German National Metrology Institute, PTB, in Germany. So, and I started there, I think, 15 years ago. So, and yeah, so I'm concerned with optical spectroscopy, especially focusing on Raman spectroscopy. And yeah, we investigate different materials from biological systems and also semiconductor materials. So, and today I want to give you an introduction about metrological Raman spectroscopy for strain characterization, especially focusing on the Raman calibration. I think that's a very important topic when we want to perform strain quantification, aiming high precision and high accuracy. So for those who are not familiar with Raman spectroscopy, I think this is a good introduction for this one. The Raman effect is the inelastic light scattering when photons interact with materials. So, for instance, here in the Stokes regime, our molecule is in the ground state and is excited by absorbing photon into a virtual state. And after its relaxation, there occurs an energy difference where the energy is transferred into vibrational motion. This is certainly the normal Raman effect, but also pre-resonance and resonance effects can occur because or regarding the used laser wavelengths, it is also possible that we can also excite electrons within the materials which then interact with our phonons. So here on the left side, you can see a standard Raman spectrometer, which is made of an optical table. Mostly the manufacturers equip their spectrometers now with piezo tables to receive high lateral resolution. And also because they combine their spectrometers with AFM. Then, of course, there's different optics. For instance, holographic notch filter or edge filter to reject the Rayleigh line from the inelastic light scattering, and the inelastic scattered photons are then focused into the Czerny-Turner spectrograph. Nevertheless, these photons are then illuminated onto the CCD, and we will get a dispersive Raman spectrum, for instance, here, the silicon phonon peak. So when we perform Raman spectroscopy, we illuminate our samples with a laser, for instance, helium neon laser, or more often solid-state lasers in the range between UV and visual range, using, for instance, 532 nanometers. Is something about 2.3 electron volts. Yeah. So, and if we excite phonons, we do this in the reciprocal space near the gamma point. So, and we receive in this way Raman fingerprint. Raman fingerprint means that the Raman spectrum, within the Raman spectrum, there appear different peaks that belong to the space group or point group symmetry of our material. So, for instance, here at the gamma point, around almost 80 millielectron volts, we observe the transversal optical and longitudinal optical phono mode of silicon. It is a three degenerate phono mode. So which means that both optical phono modes are superimposed each other. Yeah. So, and we observe only one average phonon peak. But if we apply strain in a certain way, we can lift off the symmetry, and we observe, for instance, phonon splitting. So, yeah, if we consider the Raman peak, we can extract different properties from our material. For instance, the line shape is can make statements about the crystallinity, the disorder function, as well as whether there's Farner resonance or confinement effects. For instance, confinement effects occur in polycrystalline silicon materials, and the peak position is related to strain. So let's talk about the lateral resolution of Raman spectrometers. The advantage of Raman spectrometers is, yeah, they are non-destructive. But honestly, you have to be very careful because if you apply the right laser power, you are able to destroy your material. Especially when you're in the right absorption range, where the absorption coefficient is high of your material. So by considering the Rayleigh criteria, so you can estimate the lateral resolution of your Raman measurement by considering the used objective and also the used laser excitation wavelengths. So, and I think regarding 532 nanometer laser, theoretically, we can say, okay, it's around about 200 to 300 nanometers, but that's not really the case, because within your optics, there's also some aberration effects and so on, which affects your resolution. So generally, you're more in the range of 1 micrometer or 800 nanometers in your lateral resolution. Yeah. So when we perform Raman spectroscopy, how does it look like performing, for instance, Raman mappings on samples? For instance, here, this is a silicon germanium fin sample. We use, for instance, this VTEC Alpha 300 Raman spectrometer. We choose certain sample area, and we start to map across this fins. So, and the main problem by considering these measurements is the amount of data that will be produced. Normally, high-resolution Raman mappings will share about 10 to 50,000 spectra that has to be evaluated. Yeah. So, and that's why we have decided to the manufacturers offer different software tools where you can perform the spectral evaluation of this, but sometimes it's rather a black box, and that's why we decided to create our own software, yeah, so that we are able to evaluate especially measurement uncertainties. And with this data, you get a Raman mapping. You can also evaluate this in a histogram to see the normal distribution of the peak position. And with this data, you can try to convert this into strain values. Yeah. I will show some details later about this one. Yeah. So it's our working group within the PDB is also searching for new techniques that will be offered by the manufacturers. So, and what we observe now is that they extend their Raman spectrometers so that they can perform Raman measurements on large wafer scales up to 300 millimeters. Yeah. So, and it's very interesting. We observe this at Horiba, VTEC, and also Renshaw offers this one. And by the way, also IBM is also interested in characterization of silicon germanium materials by using inline Raman spectroscopy, and that's also very interesting for us. But the problem that we have noticed is that the calibration, there's a Raman calibration can be different from the manufacturers. So, and we see that there are some space for optimization and maybe to introduce regulation how to perform this for this inline processing. Yeah. So, and also NIST, the colleagues, our colleagues from NIST, they also want to introduce strain standards for Raman spectroscopy and also for the industry. But I think this takes some time because you have to validate this, on an international level by doing round-robin comparisons. And so in this way, that's the status of 2023. They offer so-called artificial strain samples. Yeah. So when we talk about strain, how can we determine strain by using Raman spectroscopy? And honestly, there is not. This depends on your material. Yeah, so it's not possible that you can apply this technique to every material. No, you have to consider the geometry of your or the crystal geometry of your material, and also what kind of strain you want to apply to your material to, for instance, extract the Raman strain response function, which is very important for strain Raman calibration. So, for instance, if we take a look on this picture here on the left, this is silicon cell depicted here. So, and if we apply an external force here in the center, the crystal cell is relaxed. Now we can apply, for instance, tensile strain or compressive strain. So, and what we observe in the Raman response is a shift of the silicon phonon mode, whether to lower wave numbers or to higher wave numbers, which can be then then related whether to tensile or compressive strain. So, and when we want to calculate the strain, we have to consider, okay, our Raman setup, whether we use polarizability or Raman in the polarizability mode, so applying polarization Raman spectroscopy, and also from which direction we apply strain. For this, we have to solve the secular matrix of this one, which is the relation between the applied strain and the phonon deformation constants. So, and by solving this secular matrix, we have to calculate the eigenvalues, which are then related to the polarization setup that we use. Yeah. So, and the strain that can be then estimated is then converted by using the Young modulus, so that we get stress values. So this is an example here, typical example that is used in Raman spectroscopy. So here, this is a silicon sample, and we have introduced a Vickers indentation, I think with a loading force of something of, it's not 200 Newton, it's 200 millinewton, sorry. So, and then we apply Raman mappings. And here on this picture, you can see both two informations. For instance, the peak position and also the peak width. So, and both informations are very important because the first one is related to strain, and the peak width is related to the morphology. Yeah. So, and if, for instance, high crystalline silicon has a phonon peak width of something about 3 wave numbers. So, and if the peak width increases, so okay, that tells us that the phonon lifetime decreases due to the change of the crystallinity. In this range, blue regions rather indicate that this is polycrystalline or nanocrystalline material because it is destroyed by the Vickers indentation. Yeah. So, and around the Vickers indentation, we observe phonon, the change of the phonon mode position, ranging up to 522 wave numbers. The relaxed phonon mode of ideal or pristine silicon, something about 522.5 wave numbers. So, okay, you can see here now you can convert this by using performing this quantification that I already mentioned in the slide before. So, and then you can extract the stress and strain fields. Yeah. So, and then you can say near the Vickers indentation we observe compressive strain, and what is also interesting is that nearby the indentation corners we observe tensor strain hotspots. So when we perform such measurements, is very important to clarify the requirements that are necessary for this. Yeah, and of course we need high temperature stability so that there's no change in the optics that maybe could introduce a misalignment of our Raman calibration. So, and also the laser wavelength stability of the Raman excitation laser is also very important. So the laser stability or the measurement uncertainty of the laser stability should be, of course, lower than the spectral resolution of our Raman spectrometer. Yeah. So, for instance, if we observe a drift of 0.01 nanometers in our laser excitation wavelengths, then this introduces phonon shift of 0.35 wave numbers. So that's quite high, quite large. Yeah. So, and the accuracy and the precision of performing strain measurements by using Raman spectrometers depends also on the spectral resolution, and the spectral resolution in Raman spectrometers is defined by the entrance slit, the width of the entrance slit, the order of the used grating, and the focal length between the last or concave mirror to the CCD detector. Yeah. So, and of course, the higher if the focal length is quite high, then your resolution is also quite high. For instance, by using a T64000 Raman spectrometer from Horiba, you have a focal length almost of 2 meters, which is, I think, but state of the art or the highest resolution that is available from commercial manufacturers. Yeah. So, and also when we now take a look on the characterization of stress and strain by using Raman, it is also possible that we can extract the strain values from different materials within one measurement. Yeah. So, for instance, here we have introduced Vickers indentation on epitaxial graphene. So this graphene grown on silicon carbide, 6H silicon carbide. Here, this was carried out by our colleagues of the Czech Metrology Institute with a loading force of 300 millinewtons. So, and here you can see in this picture the silicon carbide terraces. Yeah, and on top of this, there are you will find graphene. So, and the pictures here show the strain values, the extracted strain values from silicon carbide and graphene. And here we use the 2D peak of graphene in the Raman spectrum, and in this case the FTO peak of silicon carbide. So, and what's interesting is that of course the strain response in graphene is approximately 10 times higher than in silicon carbide. So, and the strain values are rather localized, laterally localized around the Vickers indentation in silicon carbide, but the strain area is more extended in graphene. So you can see the red areas are related to compressive compressive strain. Yeah, so and yellow areas we don't see this here is rather a tensor strain. So and of course, what's more important is that we can also investigate within one Raman spectrum the lattice defects by considering here this D peak. It's called defect peak when we introduce lattice defects or point defects in graphene, and we can see, okay, that the Vickers indentation has introduced lattice defects or a certain lattice or defect density in graphene. So, and when we take a look on this picture here, I try to hurry up a bit. So we see that different techniques are applied to investigate the strain response in graphene or other 2D materials, and we see that the strain response can be different on the used setup. Yeah, whether we apply biaxial strain or uniaxial strain. So, and the main problem in graphene is that normally strain cannot be extracted so easily because we observe a superposition of strain and charge carrier doping due to the resonance states in graphene that is excited by our laser. So in this way, we have to perform a spectral deconvolution. This is shown here, where we use the G and 2D peak and perform a vector separation so that we receive a strain doping trajectory, where we can now estimate the strain in doping amount. So yeah, this is something that we also have carried out on in our own research. So we have investigated by applying this technique the change of the buffer layer into a quasi freestanding monolayer graphene by intercalation of oxygen. So, and as you can see, we can extract defect densities. So the material after the intercalation reduces its defect density, but on the other side, we apply more and more strain by introducing more and more heat into the sample. Same situation by liquid metal intercalation. Here we intercalate, for instance, indium or gallium atoms between the confinement space between the buffer layer, graphene buffer layer, and silicon carbide. And by applying Raman, we can now extract some properties about the doping state and also the lattice relaxation of the buffer layer after the graphene or gallium intercalation. So a big problem. This strain response curves are extracted by using so-called Grüneisen parameter, and the Grüneisen parameter is the relation between the phonon change and the volume change of the material. So, and you can find in the literature different values or a lot of values related to different materials, but also some well, we are also facing some problems that the values, the Grüneisen parameter can or show some verification or some deviation regarding the used strain measurement setup. Yeah, so and that's a big problem if you now want to perform some strain measurements. Yeah, it's on your own which value you want to choose. Yeah, so and that's also a point that we think that needs to be improved. So, and this also depends, of course, on Raman spectral calibration technique. And here you can see 3 different techniques that is generally used in Raman spectroscopy. Yeah, I think the most famous one is the 1-point calibration by using the silicon peak, but honestly, that's not. This is an insufficient calibration method because you're only performing 1-point spectral point calibration, but you don't know the measurement uncertainty, which is lower or higher wave numbers considered to the silicon phonon peak. So this is not applicable for strain measurements. On the other side, there is some recommendation by the ASTM performing Raman shift spectrometer calibration by using reference materials, for instance, polystyrene, sulfur, or cyclohexane. That's, I think, a good opportunity, but however, the standard deviation is up to 2 wave numbers. That's also not acceptable for strain quantification. So, and the best way is in performing Raman calibration by using plasma lines or gas emission lines. So here you receive the highest spectral accuracy and precision in Raman spectrometer calibration, which is normally lower than 0.5 wave numbers. So, and you can find the reference lines, for instance, of neon, krypton, and mercury by using the NIST database. But the problem is that you need to know the exact wavelengths of your Raman excitation laser for this, yeah, because you have to convert this from relative wave numbers to absolute wave numbers. So, and also the point that Raman spectrometers of the different manufacturers use different calibration techniques. For instance, here VTech uses fully automated Raman calibration system. So this is a rather user-friendly method, but yeah, it's a black box method. You don't have you're not able to adjust the calibration results after this calibration procedure. Of course, you can perform manual Raman calibration. For instance, here Horiba makes this available, but of course, this is not suitable for inline processing in semiconductor industry. So, is there an alternative approach? Yes, we think there is an alternative approach. In 2020, Ito et al., colleagues from the Japanese National Metrology Institute, has published an article in the Journal of Raman Spectroscopy, calling this reliable estimation of Raman shift and in its uncertainty for non-doped silicon substrates. And yeah, they offer this as certified reference materials that they now offer for silicon samples. What's the principle of this technique? Yeah, they when they investigate silicon phono mode, they also introduce gas emission lines or plasma lines into the spectrometer, so that they are able to monitor both the silicon phonon line and the neon lines here, for instance, within the measurement. So this is called bracketing. Yeah. So, and these exact peak positions of the neon lines are known. So you can find this in this database. So, and the measurement uncertainty is lower than the Raman sensitivity. And of course, by applying this equation here, you can correct the silicon phonon peak to the exact position. Yeah, so in this case, if there is a misalignment in your calibration, Yeah, so you can correct this by using this technique. So if you take a look on this equation, you see that they measure the ratio between two lines, or the distance between two lines, neon 2 and neon 3. So, and they take the ratio between the theoretical and the observed value, and then they correct this in this way. So, and they also have performed the calculation of the measurement uncertainties by using GUM as proposed by PM. So that's really great. So, and have also taken notice what measurement uncertainties have a certain impact of your of this measurements, and they found out that the grating dispersion has highest impact on the measurement uncertainty, and they were able to receive or to calculate a measurement uncertainty of 0.28 wave numbers with a coverage factor of 2. So, and they stated that this technique is applicable for helium neon lasers. Yeah. So, but they also left space for those who, for the situation when you want to use, for instance, other lasers. The main problem, or what they stated, is that the measurement uncertainty of the laser is negligible because the wavelength stability of helium neon lasers is quite high. So, and the wavelengths of helium neon lasers are known and are also listed in the database of the BIPM. So, and that's why we decided to extend this method so that we can apply this method to solid state lasers. Yeah. So in this case, we had this idea that we introduce that we use pen rays. These are gas emission lines from this bulbs, and we use different types of pen rays that are filled with, for instance, krypton gas or mercury argon gas, and we couple both lamps into our spectrometer here. Here you can see on the right our setup, and we use optical fiber that we introduce into our spectrometer. So this is also shown here on the on this slide. So, and of course, the main problem is our aim is that we want to compare our measured gas emission lines in the Raman spectrum with the NIST database. In this case, we have to convert the relative wave numbers into the absolute wave numbers. So, and in this case, it is necessary that we have to also monitor the wavelengths of our laser. And in this case, we have equipped our system with a wave meter. So where we can then determine the wave number or the wavelengths of the neodymium YAG laser. So, and which is shown here by using also a fiber optical system. So, and this is the result. Yeah, here you can see the silicon phonon mode. Now the silicon phonon mode is is also in a certain bracketing situation, enclosed by the spectral lines of mercury argon and krypton. Yeah, so it's the same procedure as stated by Ito et al. So, and I think the most the big advantage of this one is that you can use different types of this pen rays and create a certain gas emission line mixture by using different pen rays. So, and you can adjust the system depending on the used laser excitation wavelengths. Yeah. So this makes the system also applicable for instance, using UV lasers. Yeah. So improving the calibration. So and in this way, we performed also with the wave meter the stability measurements of our laser and found out, okay, that the exact wavelength is something around 0.2 nanometers with a standard deviation of 0.004 wave numbers. Yeah. So yeah. That's the main concept that we have also introduced within the challenges project, and that we also use in our round robin. And as I mentioned before, we are also focusing on silicon germanium, and we think that by using both this calibration technique and also yeah. Making comparison measurements within the project, focusing on silicon germanium, we are able maybe to introduce a standardization for Raman calibration and also strain Raman calibration procedure that maybe could be proposed to the ISO TC committee. Yeah. So the most important thing is in silicon germanium that you can tune the strain levels by changing the germanium content, so which results into different strain levels. And by using Raman spectroscopy, you can measure then the difference in the between the strain in the silicon strained silicon layer and the relaxed photon modes in the silicon substrate. By measuring the spectral distance between both peaks here as shown, you can estimate the strain. So and this is carried out here in the challenges project, and we have started in performing the round robin by measuring this delta omega. So and as we can see here is the first results of this measurement by on sample 1 with the highest germanium content, and is what we observe here is that the scattering of the data points is within 1 wave numbers. Here you can see the different partners. Now it's currently PDB and CEA, but we extend this. Other partners will also have also joined this round robin and will share some data. Also external partners, for instance, Technical University to Braunschweig. So and what we see here is that the data points are very close together, except this one here. The first one on the left, this is related to the Xanthera spectrometer from Bruker Optics. And here I have to make a statement. This is rather it's a spectrometer with a rather low spectral resolution because of its extremely low focal length. So and we expect that this type of spectrometer are not applicable for this type of strain measurements. So and if we skip this data value, then we are in the range of 0.5 wave numbers, which is very promising, I think, also for sharing this data to the ID work item to the national mirror of TC 210. Yeah, that's it. Any questions? Great.
So thank you, Stefan. And now Mm. Yes. Okay. And now let's welcome Yovav and Shira from Nova.
Thank you. All right, so hello to everyone. My name is Yovav. With me online is Shira. Shira, if you can say hello just for the sound check, so I know you're with me. Obviously, that didn't go so well. Hopefully, Shira is with us online.
Hi.
And,
Yeah, I'm here. Yeah. Hi.
All right, and the sound works fine. We can hear Shira.
You can hear me? You can see me?
Now we can hear you, but I don't know if we can see you. I don't know. Maybe when you speak, the system will automatically shift to you. We will see you in when your slides.
Yeah, we can see you. We can see you. Online, we can see you.
Okay.
Even better.
Yeah.
All right. So the three speakers that you just heard, they represent Nova, Nova Ltd, headquartered in Israel with subsidiaries abroad. And we'll talk about our tool is called Ellipson. So Nova Ellipson, in this case, Raman combined with machine learning. I want to introduce this approach of how to combine Raman with machine learning and demonstrate it with a use case of boron doping detection, characterization in silicon germanium alloys. If I ever say SIGI, I mean silicon germanium. I'm used to saying SIGI. How do I flick with this? Okay. So in this talk, we'll introduce the idea of Raman machine learning. The problem statement is Nova's market, what we're trying to do with this technology, a demonstration, and in the final slides, I'll tell you how this has to do with the challenges project and how this has to do with TERS, deep enhanced Raman spectroscopy, that we heard about mostly yesterday. So here you see on the top right corner, this is the Nova Ellipson tool. Unlike what Stefan before me told you, and also some speakers yesterday said that this is a lab-based tool or that it's offline. Nova's tool is inline, meaning that it's in the fabrication floor. It's a high throughput. It works on 300 millimeter wafers with the leading manufacturers that you're all familiar with. This tool has been on the market, I believe, since, Amiad, correct me if I'm wrong, 2019 or 2020. That's more or less when it came on the market. And since then, it's been going on to a second generation and other generations. And here you can see it has 3 load ports. So this is a high throughput tool. And so far, it has not been coupled with machine learning, but recent work has combined it with machine learning. And that's what I'm going to tell you about. So it's fast, high throughput, fit with semiconductor manufacturing standards. It's non-destructive. We take care, Stefan, we take care not to burn the sample, as you said. If you use a too powerful laser, that's not good. The clients don't like it when you fry their wafers. Yeah. And here's an example of what we're trying to measure. So this is, in the illustration, this is a nano device. On a nanometric scale, and like Stefan showed you, the spot size of the far field, the Raman spectrometer. Keep in mind, we're not talking about Raman imaging or micro Raman microscopy. We don't produce an image; we produce spectra. So the spot is about 1 micron in diameter. You will never be able to resolve this nanostructure. It's only a few nanometers side to side. And the question is, how do you do that? In this case, the nanostructure has critical material parameters, such as the strain, the composition, the percentage of germanium, the boron doping. It's highly critical, as it says in the slide. The doping is the Doping is the introduction of impurities into the semiconductor crystal, the silicon germanium crystal. Usually the manufacturers use boron and phosphorus. The doping level increases the conductivity by a factor of many magnitudes, up to 1 million. And that's what makes inline dopant detection and metrology, meaning the measurement. We need to give a precise measurement of the concentrations in real time and let the tools know. If you remember yesterday's talk by Delphine, the metrology tool is in between the other tools that are doing the process step. And so this tool needs to report back to the previous tool how much doping was introduced, so that they can, in real time, close the loop and fine-tune the process step based on the metrology information. So these kinds of structures or these kinds of materials will be placed deliberately on the scribe lines where they have a large enough area that the NOVA tool can navigate to and fit its 1 micron diameter spot into the scribe line and get that kind of a measurement. And in some cases, we can do it on the device itself, but usually metrology works on the scribe line, on the sacrificial scribe lines. Before we continue, I need to introduce a few things. Until the point we get to machine learning, I need to introduce a few things so you'll understand the use case and the experiment. So I have to introduce to you the lab SIMS. I don't think it was discussed until today. It wasn't discussed here yesterday. SIMS, so that's a secondary ion mass spectrometry. Basically, you bombard the wafer with ions, and they spit out secondary ions. Basically, you're mining through the wafer, right? Imagine meteorites of ions hitting the wafer, spitting out material from the wafer, and you're digging into the wafer. And as the secondary ions are impelled from the wafer surface, you collect them and you measure their mass spectrometry. Mass spectroscopy. Sorry, blacking out. You're measuring their mass anyways. So you can characterize the species of atoms that are in the wafer from top to bottom. You get the Z resolution. Okay, you know from each depth what is the composition there. And so SIMS, because it works the way I described, it is usually in the lab, usually not inline, because you're hitting the wafer. So this is destructive, and it does induce contamination, and you're sacrificing that spot at least. So that's a lab tool. Traditionally, so it's used for detection of dopants and impurities. The wafers have to be taken out from the fab line, sent to the lab, cut into these coupons. Most SIMS can't handle a 300 millimeter wafer, only coupons. And the time to results takes weeks, traditionally speaking. So that's why it's not an inline, not a real-time process tool. There is the exception though, the last bullet. Nova's Metrion tool is the exception. It is an inline SIMS. Forget everything I told you about how it's dangerous and contaminating. Nova did manage to introduce an inline SIMS fit for 300 millimeter wafer. And I checked yesterday, this was announced January of this year. So this is a brand new tool. Don't ask me about the sales, I'm not up to date. But traditionally, keep in mind, for the sake of this demonstration, think of a lab tool that you cannot introduce to the fab, but you do have in the fab the Raman Ellipson tool. And the question is, can machine learning help me connect these two tools and effectively introduce the lab tool into the fab? All right, I'll take a measurement in the fab, ask the machine learning what the results of the lab tool might be, and give a prediction. Don't worry if you didn't get that, we'll get to it in a second. So why should we use Raman combined with machine learning? As we've heard from Stefan and other speakers yesterday, Raman spectroscopy has been explored for multiple metrology use cases. It is a very rich, information-rich metrology concept. It gives you material material sensitivity to material characteristics that are critical for the manufacturers, and they would love for you to report on that data and to tell them what material they have manufactured. A lot of speakers did, Stefan also emphasized that the signal interpretation, that this spectral signal needs to be interpreted into something that's relevant for the manufacturer, some physical parameter or chemical, stoichiometry, doping. Somehow you need to translate this spectral line into physical, material, chemical properties that you can report on. And that is essentially the mission of metrology, is to make a measurement, not only to tell you if you're deviating, but actually to quantify and give you the measurement. Silicon germanium boron doped epitaxial layers are a challenge for this metrology, because here the vendor, the manufacturer, the fabs, they would like us to tell them about the germanium percentage, germanium composition, the boron doping level, the strain, etc. Like also the thickness. These are many parameters that they would like us to report on. All of them, or some of them, are somehow encoded in this spectrum, and we'll need to find a way to extract that information from this spectra. We have other information, but let's stay with this. And so yeah, so Nova machine learning has made this possible. That's the claim. Here in this graph, we show you typical Raman spectra from several wafers. There's about, I don't know, 7 or 8 wafers here with a DOE, like they were deliberately manufactured with some differences between them. They're varying in the boron doping level, and you can see that Raman can definitely tell them apart. We can distinguish, we can differentiate between them. The question is, can we extract numbers? Can we quantify the amounts? So I hope I defined enough. The motivation is to combine machine learning with the Raman approach. We want to collect the spectra, feed the data into the machine learning infrastructure. ML, wherever you see ML in this slide, ML is machine learning. So the data goes into the machine learning. Machine learning needs to create a model. Sorry, I didn't introduce what machine learning is, but basically the simplest way I can describe it is think of a child, and you show the child cats until the child has a concept of what a cat is. The next time he sees a cat, he says, "Oh, that's a cat." Okay, so take a child, show them sufficient numbers of spectral graphs, and they'll have a model in mind. They'll have some conception of Raman metrology, and then the machine learning model needs to be tuned, needs to be trained, like what I just described, until we have a model that we can work with. All right. After the child has developed a concept, the child is now can execute functions. So the challenge for machine learning Raman is that, well, there are many optional machine learning models. There's many ways of doing this. Not all of them will work optimally well for this use case. So there's a need for some expertise in data management and machine learning modeling. And also the data volume is usually low. Right? Imagine a child.
I think we need to switch to Shira, no?
No, thank you. I will switch to Shira as planned. Thank you.
Okay.
Thank you. Imagine, sorry, I got distracted. Oh yeah, the data volume usually low. What I mean by this is that to train the child, let's say, you need to show them many cats, right? So to train this machine learning, we need to show them many spectral graphs and the lab reference data, like the grand truth data. But we don't have a lot of wafers that we can send to the lab and cut up into coupons and sacrifice and really exhaust the expensive SIMS tool or the TEM that we heard about yesterday. These are expensive tools. The wafers are expensive, so there's not that much data. Plus, the Raman machine, the Ellipson tool, does not scan the entire wafer, cannot give you these, it could, but we don't use it in a way that Stefan described. We can't scan the wafer and give you a whole map. It is not designed for that. It's designed to work fast with sparse sampling near the wafer center, near the wafer edge, some scattering, and move on to the next wafer. So how to do this kind of machine learning training with sparse data? That's the major challenge. The solution, here I'm going to give it to you really in high level. Don't worry if you don't catch it, because Shira is going to give you the details later. But generally, in high level, I'm going to give it my best. We want to optimize a wide range of algorithms, machine learning algorithms. We want to rank them. I'll show in a minute. I'll show you how. Rank the various, consider competing models, and we want to rank them. Select the highest ranking model according to extended metrics, right? We want to have a standard by which to judge which model works. So we call that a metric. We want more and more and more of these metrics, more and more of these standards. To extend, third bullet, we want to extend the data volume by considering labeled and unlabeled data. I'll define that in the next slide. With user-defined weights, we rank, we select, we tune and train the models using these extended metrics. That's the next slide. In a minute, you'll get it. And we have a user-friendly interface for scientific workflows to make this useful for the user. A little bit of a repetition, but I think it's critical. So as I told you, we deal with sparse data. We have very small volume of labeled data. Labeled data, some of you might call it reference data. This is the lab tool, the external, the not Nova's information, somebody else's information. SIMS, TEM, X-ray, whatever it is, the reference data. Then we apply machine learning on the sparse data, which creates the problems. If you do machine learning with sparse data, you have unreliable models. Like that child is confused what is a cat or what is not a cat, because not sufficient data was introduced. So you'll get unpredictable, unstable solutions. Our approach is to use unlabeled data. Unlabeled data, if it exists, it is your own data. You add your own data to the volume, to the silos of data, such as tool-to-tool data, repeatability data, full wafer maps. You yourself inflate the data volume, and that gives you these extra matrices, metrics, to do cross-validation of your machine learning model. I know that was not totally clear, but hopefully you got the idea. And you use that for model selection based on the additional unseen data. And another innovation here, that we find that it works well for the distribution rather than the value of the measurements. So Shira, please take it away.
Okay. Hello, I'm Shira. I'm a data scientist at Nova. I will present to you the results regarding boron and germanium concentration machine learning here, the work we did. So next slide, please. Okay. So the first results I will show you are cross-validation results for boron concentration. We used the SIMS reference. I've already explained to you what is SIMS. We used here expert features data. Basically, when we are taking the spectrum, which is our data, we can use it with two options. The first one is take it as a raw data, and the second is to extract features from it. So in this case, we extract features from it. You can see here on the right-hand side, the models we tried from top in the left to worst on the right. We can see that the first model, the best of our model, is a linear model, but the other top models are non-linear, which is very interesting in my opinion. You can see for each model, you can see distribution. This is what Yovav explained to you before. Because we're dealing with small amount of data, usually we decided to calculate the distribution for each model. This way we can see the whole range of scores this model can produce. and then we can know and be certain that our model won't be produces much worse scores. So when we choose model based on this its distribution, we believe it will be more robust. Next, we can see here the matrices we use to evaluate our models. Here is presented the matrices for the top model. You can see it normalized with normalized mean plus minus STD. Again, we used the STD because we want to see the whole range for each metric, because we want to be certain that in each metrics, the scores are the worst and the best scores for each split or for each iteration will be good enough for us. So let's talk about a little bit about the matrices. R squared, RMSE, and slope are quite common in the machine learning world. The DOE is the design of experiments. It's what Yovav told you before. It's usually information that comes from the customer, and we take it as unlabeled data. This is the addition of unlabeled data for this application that Yovav explained to you before. R squared, RMSE, and slope are matrices that calculate from the reference data, the label data. Average DOE we calculate as well from the reference data, and within wafer metrics is the smoothness in the wafers, in each wafers, which we also calculated from the reference data. All in all, you can see that we have here very impressive results in all of the matrices and very dense distribution in the top models, which is exactly what we want. Let's see some plots. Next slide, please. So in the here we see plots of the top model for the boron concentration. On the left-hand side, we can see radial plot, which is the boron concentration as a radius of as a function of the radius, the location on the wafer. You can see it's colored by the wafers in the data. Now we can see great wafer separation and excellent radial map. We can see very smooth lines of the wafers. On the right-hand side, we can see a prediction versus reference plot, which is also colored by wafers. The wafers are evenly distributed across the line, and we can see high correlation between the reference and the prediction, and that the machine learning model follows the reference very well in all of the wafers. Next slide, please. Now I will present to you the results of the germanium concentration. Next slide. Okay, so again, our reference data is SIMS, and we used here again in expert features data instead of the raw spectrum. Here we can see that the top models, the top 5 models are linear, and they have very dense distribution, which is very good for us because we want to choose the model with the most dense distribution. This way we can be sure that the results won't be very far from each other in each iteration. We can see here again that all the matrices, they have extremely high performance in all of the metrics, and that all of the models are linear. Next slide. Here again, we can see the top plots for the model for the germanium concentration. The radial plot again is shows very excellent, very smooth wafers and excellent radial map. And the prediction reference plot showed very high correlation between the reference and the model prediction, and that the machine learning model managed to follow the reference very well in almost all of the wafers. So we get very nice results in both germanium and boron concentrations on the Raman data. That's it. Thank you.
All right. How to go back to the slide?
Yes.
All right. So in my final slides, I want to connect all the dots and tell you a little bit about the challenges of challenges, the consortium challenges, what this has to do with tip-enhanced Raman spectroscopy, and what is the aspiration for machine learning moving forward. All right. So in this consortium called Challenges, there was progress made with respect to tip-enhanced techniques, such as TERS that we heard about from Aaron Lewis yesterday, speaking for Nanonics. The appeal of those tip scanning techniques is that they offer high resolution on the lateral surface, high lateral resolution with tailored sensitivities. Aaron Lewis described yesterday his innovative tips, and he has many more. So these tip-enhanced, all these AFM-based techniques can offer you diverse sensitivities to diverse POI. POI is parameters of interest to the manufacturer of the wafers. You have precise localization. You know exactly where you're looking and where you are measuring your measurement. Unlike the Raman tool, the far field, which is 1 micron, you don't know exactly. You're getting the whole contribution from the whole surface area. With these AFM-based techniques, you can have 3D mapping, more than just one spectral graph. However, the adoption of lab tools such as the SPM and the SIMS and the TEM, the adoption of these solutions to the inline, they suffer from risks. In this case, contact with the wafer and contamination. For example, if your tip is coated with gold, the manufacturers don't like the gold in that environment for contamination reasons. So that stays as a lab tool for now until that is solved. And while the far field, the Nova Ellipson Raman tool, is a non-contact metrology system. It's safe, it's fast, you get the solution, it's in real time, it's inline, it's already deployed in leading fabs. So we want to be able to link these two techniques using machine learning algorithms. And so the question that we posed in this consortium was, can we train the far field Raman Ellipson tool? Can we train that based on the near field tip-enhanced Raman spectroscopy tool made by Nanonics? And to bring those benefits from the lab into the fab. That's here in the graphics. I remind you what we heard yesterday about the near field tip-enhanced Raman spectroscopy. We have the tip coated with some conductive materials for the plasmonic enhancement. When it's in contact or near contact with the surface, you have the Raman enhancement, the plasmonic enhancement, and then the tip can move up or move out, or anyways move away, and all you get is the regular Raman signal. Aaron Lewis of Nanonics showed you yesterday in one example that we worked on with graphene from Graphenea. There was a shift between the far field peak and the near field peak. We suspect that probably the tip was close to maybe a defect or something was happening there at the surface that was enhanced from the perspective of the near field, but blurred out from the perspective of the far field. And the question is, could we have made a scan with the near field, made a scan, gather some statistics about where the peak is statistically, and compare that to the far field, and in theory, be able to predict from the far field what is the concentration of defects on the surface, for example, or any other kind of statistical data that is accessible to the near field. Could we predict that from the far field? So that's what you see in this flow. The near field gives you the scanning research in the lab, slow pace, take your time. The far field ellipson inline with machine learning together, we could give you a material metrology with new types of offerings, such as parameters of interest having to do with distributions, statistics. A few speakers today and yesterday spoke about how when you have a fin silicon germanium crystal, and it is strained. It has relaxation on the edges, in the corners, stuff like that. Changes and variations that happen on a nanometric scale. Not seen from the far field, but they are seen from the near field. Can we bridge that gap using machine learning? That was the question. And we showed you that theoretically it can be done with SIMS. That's what Shira explained to you. In theory, it could be done also with tip-enhanced Raman spectroscopy. And we really hope to be able to do that with the time remaining in challenges or in the future beyond challenges. So the future work, this aroused the appetite, and we're following up with these results. We're having an ongoing market research to interest our clients in machine learning for Raman to make this penetration even better. We can tell you already that we would have to customize for each client because each client grows their silicon germanium crystal in a different method, different outcome. You would have to train your machine learning model for that client, and that client, it's recommended that the client would give us a wide range of concentrations so that the machine learning can really be trained on the entire variety and be able to give you good predictions. And of course we will need so we're interested in extending what was demonstrated here for SIMS, to extend it also to tip enhanced and to extend it to other metrologies to be able to extract other parameters as much as possible. Okay, so regarding TERS as the reference tool, in this particular case with challenges, the parameter of interest, the POI, it goes beyond the germanium and boron concentration averages, right? The Raman far field just gives you averages. We wanted to go one step beyond and to give you, for example, chemical variation statistics on with a lateral spread. We tried to do this work with graphene samples, and we tried a little bit to do that with the DIVA samples to give you the strain distribution profile mapping on the fin from side to side to find those relaxations at the edges. And we have other appealing applications such as tip-enhanced Raman spectroscopy on 2D materials for defect detection, defect classification. There's many varieties of defects. We would like to be able to differentiate between them and to quantify them. For that, we would need to train the Nova ellipse on far field, train it on the reference data provided by the TERS statistics, use machine learning to predict defect statistics, distributions by far field in a non-contact measurement. And this is, I think, the final slide. This is the vision that we're already starting to see materializing. We have the Raman inline tool. Where's the SIMS? There's the SIMS. So that we were able to couple these two. One of them is the lab tool, one of them is the inline tool. We were able to couple them with machine learning. And we should be able to find use cases where the tip-enhanced Raman can serve as the reference data, or any one of these other methods, XRF, XPS, or the client can give us other information without measuring. And that's the promise of machine learning for using in the inline. That's it. Thank you very much. We're open to questions.
So we have a question on the chat.
Can I have a question, please?
Okay.
There's also Stefan. Yes. Just say which one you want to go first.
Van Hoa, you can go.
Yes, thank you. Thank you very much for your very nice presentation. It was very impressive to me. And I have a few quick questions. So for example, when you're training your machine learning model to calculate the concentration of the germanium, for example, so I want to know which parameter you use. So which spectral parameter you fit the model in this case? you use several parameters or only single parameters or?
No, there's a bullet here. Yeah, I thought this question was coming. There's a bullet here that's it's encoded. It says expert features data. What we mean by that is that we have algorithms. We have physical-based, rigorous physical-based algorithms that look at the spectral graph and extract these spectral features, such as the peak intensity, peak position. I don't want to reveal too many things, but lack of symmetry of the skew or the ratio between the peaks. So we have algorithms that take the graph and they can extract these spectral features. And Shira discussed whether that is beneficial to use these extracted features or to use the raw data. The entire graph is raw data. So we find, in this use case at least, we preferred using the expert features data, right? The algorithm tells us, the rigorous algorithm extracts the data, and that is fed into the machine learning algorithm. Does that answer your question?
Yes, okay, thank you very much. And the second question is, actually this Raman signal is can affect simultaneously with several properties. For example, strength, doping, the crystalline quality, and also the concentration, as you already showed. So for example, so here I want to know that in your machine learning based model, if the simultaneous effect is taken into the account for that or not. For example, when you have like a wafer, you don't know about the strength, you don't know about the concentration. It is possible to get both information from the machine learning model or only one concentration in case you have several like unknown properties, for example.
No, so in this case, it's more than that. It's all of what you mentioned simultaneously, plus because of this method that we showed here, we add to the data our own unlabeled data. I hope that's clear what we mean by that. We add our own machine. For example, it's specified here: the tool-to-tool data, repeatability data, full wafer map data. So we add more data, and the machine learning prediction not only answers your question of germanium concentration, boron doping, strain, it also answers this data. It also predicts the full wafer map and the repeatability, etc.
Okay.
And we use that as cross validation. Okay, we can compare that to our own data because we have access to our own data. So we do cross validation in order to identify which model works best. Is the distribution narrow? This is what we emphasized here in the last bullet, that we look at the distribution rather than the value in order to identify the right model. All right.
Okay.
And in this use case, it worked. This does not mean, because machine learning is a little bit like a magic every time it works. You shouldn't think that this would work for whatever challenge or for whatever task you want it to work. There's no guarantee, but there's hope.
Okay, I see. And the last question is, are you mentioned in the slide that you can fit your machine learning model by tune to tune data? That means you can fit the model by the data obtained by another equipment, by another instrument, right? Not only from the NOVA equipment. Is that correct?
I would say refer to my last answer. This gives you hope. This gives you inspiration. I don't know how to say it. In theory, if there is a correlation between the inline tool and the lab tool, if there is some physics is going on behind the scenes that we don't know how to capture yet, there is hope that the data will be correlated such that machine learning would capture the correlation and give you that predictability. But as I said, use it with caution. It's not guaranteed that for every selection of tools and every kind of measurement, you would be able to create the machine learning model that would work well. It can give you nonsensical predictions also. So I don't know what you have in mind, but depends. I mean, good luck.
Okay. So I'm not a specialist in machine learning model or something like this, but when I see your results and your presentation about the capability of the machine implementation of machine learning, it was very impressive to me. And then I hope that in the near future we can like do some demo with your tool or perform some tests with your tool. Thank you very much for your presentation.
My pleasure. Here you have the name Shira Soudri. She between her and I, she's the expert on the data and the machine learning. I'm also very impressed every time it works. I'm a physicist. So if you write down this name and look her up on
yes,
LinkedIn,
I already noted this name.
We'll be in touch because I don't know who I'm speaking with, but we can
I'm
get.
Van Wanley from CEI Leti. Thank you.
Okay. Here you have the three names of the contributors if you want. There was another. If we have time, Stefan had a question.
Wait, we have just one question before on the chat, so you can.
You want me to read it? Yeah. Is there a way to assess the ratio between interstitial substitutional boron ratio in silicon germanium since you are mixing SIMS and Raman, or not at all? Let me read this for a second. Assess the ratio between interstitial substitution. Can I present this? I think maybe our third speaker, maybe Amiad, can answer the question.
Here.
What? No, I wanted to
What
show
is the question.
I wanted to show the question on the screen.
Oh, sorry.
It's gonna be hard for me to explain this question. The question is there a way to assess the ratio between interstitial or substitutional boron ratio in silicon germanium?
You can read it from the chat.
Oh, he can read it. It's on the chat.
No, I'm not sure that there is a way to predict the interstitial substitution, because in Raman measurement, you measure basically only the activated boron, right? The activated dopants, where in general, you assume that basically in SIMS, you don't measure only the activated dopants. So, and between interstitial and substitutional, I'm not sure that there is a way, or I don't know of it. Who asked the question?
It's Delphine from.
Delphine.
You know Delphine.
Yeah, I know Delphine.
Okay, so the interstitial substitutional boron is the boron that is that's not a part of the lattice. It's just sitting there, not activated, right?
Yeah, this is my understanding from Delphine's question. I'm not sure what she meant.
No. Now that you give the answer, I understand the question better.
Yeah.
And yeah, so the question is essentially, let's translate the question to the following: does boron doping, if it sits in the crystal but it's not activated, does it move the signal at all? Does it move the Raman signal at all? And if the answer is no, then we will not be able to pick it up with the Raman tool. Maybe there's a Fano effect. Could that be? Could it shift the lines with a Fano effect? Let's take it offline.
Is that what you meant? Can you just say in the chat if this is your question?
Or to save face, like just take it offline.
Yeah, we can take it offline. So.
Wait, Stefan, you had a question? Can they hear the question in the microphone?
If you can see, yes. Do you have a question?
Stefan, you had a question?
My question is, how many data points are necessary for your AI to make some statements about the quality of the data?
Yeah, this is always the question. I'm usually the one who asks that question. Should I repeat?
Yeah.
The question was how much data is required. As you see, she's also laughing. She knows where the question is going. How much data is required for the machine learning to converge onto a model that is. Nobody ever gives an answer to that question, so I give myself the leave not to answer. Like, we don't know that in advance. Every time there's a new use case that comes up, somebody's going to ask that question, and we never know. But I'll tell you, in cases that I've seen presented at Nova internally, also presentations, surprisingly little data, surprisingly little data. Sometimes it's like 10 wafers, 30 wafers, surprisingly little. I don't know how to explain it. You would, my intuition would have said more, but it's surprisingly little.
Not the measurement uncertainty that has also been applied from the measurement device.
I want you to ask this to Shira. Do we have time?
We are 10 minutes late, but okay.
Ah, I thought we were early. So Shira, this question is for you.
So, hi Shiva. The standard deviation that you have shown on your slides, that's also coming just coming from your AI model. Yeah. So do you have to apply also the measurement uncertainty that's coming from the measurement device?
It's a good question. I think so. No, I think no. The reason that we do it is because we want to look at, because we're working with small amount of data. We believe that you know, when you're using machine learning on small amount of data, usually you get unstable results. For different split, you will get very different scores, and for additional of data you get, the model will change drastically. So this is why we decided to add the STD and the calculation of the distribution. So I don't think we need to look at it. It's only for the machine learning. It's only for us to trust the model we choose from. This is, yeah. Thank you.
I agree. I just add that you can use this. This kind of shows Stefan. This kind of shows the path. Like, even if we didn't take into account if I answered your question correctly, we didn't take into account algorithmically. We didn't calculate our own uncertainty about our own data or the reference data. But this is an unfinished business. This is a demonstration that was done for a client in order to entice the client to give more wafers, more data, and to enhance and to eventually go someplace. Because Nova is not in the business of making the research. Nova is in the business of making business. So this is just to show that there is practical potential here to be capitalized on. And yeah, that's it. That's what we're doing. All right.
Are there any more questions? No? So thank you all.
Thank you.
And Ivan?
Thank you.
Wait. I don't have here. Yes. Okay, just wait a second so that I can share it. Okay, thank you. I'll leave the floor to Ivan Gordon.
Okay, thank you. Okay, thank you, everybody. So I will present now a slightly different type of presentation. So I will not talk so much about characterization and nanotechnology. But as you know, in the Challenges project, we have different applications. And one of the application domains is photovoltaics, so solar cells. And I want to talk to you about what is now actually the state of the art today of this technology, and what are some of the main challenges. Because yeah, we know that we want to become climate neutral by 2050 to reduce as much as possible the heating up of the planet. And that means we really have to go to a massive electrification of all our energy. And especially wind and solar will therefore play a huge important role in the electricity production of the future. So we can start by just looking a little bit to the history. So here you see the so-called learning curve of photovoltaics. So that's actually a curve that with data that starts in 1976, and that shows actually the evolution of the cost per watt peak for a PV module as a function basically of how many of these PV modules have been produced. And we see that this curve over the 4 or 5 decades has more or less follows a straight line with a slope of 24.4%. So that means each time that the amount of PV modules is doubled, the cost is going down by 24%. So it's quite a lot. And we see actually that 50 years ago, if you wanted to buy a PV system, the panels alone would cost you $100 per watt peak. So this is huge. So imagine that you put 3,000 watt of PV modules on your roof. That's a small normal roof system. In 1976, it would have costed you $300,000 to do so. So it's the price of a house. Today we are in 2023. We are around 20 cents per watt peak. So it's more or less a factor of 1,000 that the cost has gone down. And so today for the same system, you pay $600 for the modules alone. And of course, this massive decrease in the cost of the PV technology has also given rise to the fact that in the last years, we see really that the amount of PV that is installed worldwide is rapidly increasing. So especially in the last years, you see almost an exponential growth. So this graph gives in gigawatts for a certain year, for instance, 2022, the total cumulative amount of PV that has been installed by the end of that year. So in 2022, we reached kind of a nice threshold where we actually surpassed for the first time 1 terawatt, so more than 1,000 gigawatt of PV was installed if we count all the installations until then. At the end of 2023, we are around 1.5 terawatt of PV that is worldwide active. So that's quite a lot. Now, if you look to what is the technology behind all these modules, we can say that at the moment, and it has been more or less like that over the last decades, around 95% of all the PV modules that are actually being produced and sold, they are based on crystalline silicon as the absorber material. So the remaining 5% are then so-called thin film alternatives. So typically it's cadmium telluride or copper indium gallium diselenide. But I will not talk about those today. I will focus on the silicon, the main technology. And basically here you see very simply stated how the 5 main steps, how to go from sand to a silicon PV module. So first we make the very pure polysilicon that's made into ingots. So it's very similar to the silicon material that is used for the semiconductor industry. These ingots are then wire sawn into wafers. Individual wafers are processed into individual solar cells, and then these solar cells are interconnected and laminated into the PV module. And traditionally, there were actually 2 types of silicon used for photovoltaics. We have the monocrystalline silicon, similar to what is used in the semiconductor industry. So it is a very pure material with few defects. But for photovoltaics in the past, we also used multicrystalline silicon wafers, where actually the wafers has different regions with different grain orientations. So you also have grain boundaries, so it means you have more defects. But typically, this is a cheaper material. But I will show you that at the moment, only monocrystalline silicon is used. So if we look a little bit deeper into the cost, so at the moment, we can say the cost of a silicon PV module is around 20 cents per watt peak. Where does the 20 cents come from? Well, it's perhaps difficult to see in this inset, but basically 40% of the cost comes directly from the silicon material that is used. So 40% of the module cost is really related to the wafers. And another 40% comes actually from the materials like encapsulation, backsheet, glass that are used for the module. So the cost at the moment are really material driven by the wafers and what we need to laminate and to make the module. And the remaining 20%, that is the whole cell processing and so on. So then this is in short the outline. So I will first say something about what is the state of the art and the main things happening for the cell processing, then quickly go into the module technology, and then finally I want to talk about what is now going to happen in the future and what are some of the main challenges there, especially from a sustainability point of view. So first we can go to the cell processing. So we start with a silicon wafer, and we have to process into a silicon solar cell. So I give a quick historical glimpse. So the first mass-produced silicon solar cell that started to be produced, let's say 15 years ago or so, was called aluminium back surface field. So you see a cross-section of this device here. And typically P-type silicon wafers were used for this type of material. It could be multi or mono crystalline silicon. And one of the reasons that this was a very successful first mass-scale produced device was that you could reach relatively high efficiencies of around 20%. So the energy conversion efficiencies, how much of the light you can turn into electricity. And you needed only a few steps. So this is ideal for high throughput industrial production. You have a simple process. So what are typically the steps? So you start with a P-type silicon wafer, you texture it at the front. So you make this pyramid structure that's actually to have light incoupling. So you reduce the reflection losses at the front and you trap the light into the wafer. Then you need an N-type region at the front, the so-called emitter, because a solar cell is basically a PN junction. So this is done by diffusion at high temperature of phosphorus. Then at the front, we deposit this blue layer. That is the anti-reflection coating to further reduce the reflective losses. Typically, it's silicon nitride grown by PCVD. And then typically metallization at the front and the rear is done by screen printing. So at the front, we print silver in this finger pattern. And at the rear, we have full coverage of aluminium. And then there is a high temperature step to make ohmic contacts. And during the high temperature step, you get an aluminium silicon alloy at the rear, which is actually, that gives the name to the device structure. So this forms a back surface field that actually passivates your device at the rear. But as I said, you can reach up to 20%, but then somehow, you hit a threshold because actually this aluminium back surface field that gives its name to the device is also the weak point of the device, because you have here clearly everywhere direct contact between the silicon and the metal, and this in the end still leads to quite some carrier recombination. And so once you are around 20%, you really have to do something about this rear if you want to further improve the efficiency. And so this is what the industry has been doing. So since, let's say, 5 years ago, there has been a massive shift from this aluminium BSF in industry to a new device, which is called PERC. And PERC stands for passivated emitter and rear contact. So what is the difference? So the top shows the old device with the aluminium BSF. And now we see in the new device at the rear, we have done something new. We have put this blue layer, typically it's a dielectric layer, in between the metal and the silicon. So this layer is there to passivate. But of course, we still need to have a contact at the rear. So there is a few percent of this layer that is again removed, typically by laser, so that we can have the aluminium contact. So the main difference is that here you have 100% of the rear surface in direct contact with the aluminium. In the new device, the PERC cell, it's only a few percent. So you have much less rear surface recombination, and you can go to higher efficiencies. But you need 2 extra steps. You have to grow this dielectric, and you have to use a laser to locally open it. So it means it's a slightly more complicated process, and it will be slightly more expensive because you need 2 extra steps in the industrial production. But you can reach much higher efficiencies. So typically in the lab, let's say for the champion cells, we can go well above 24%. So it's a massive jump you make from 20-something to 24-something. And so some time ago, the colleagues of Fraunhofer ISE, they made this device roadmap where actually they plot the expected efficiency in industrial production. So this is not a lab cells, but this is really the mass production as a function of the different device concepts. So for aluminium BSF, we can reach 20%. That has been done in industry. For PERC cells now, you see that indeed companies are reaching 23% in production. So probably you can go in industry to 24%. But then again, you reach a plateau. And the remarkable fact is actually that also this PERC cell, although you can go to 24%, still the rear surface is the limiting factor. This few percent is still a problem once you reach 24%. So if you want to go even further, we have to do something about these few percent of direct contact between the silicon and the metal, and we have to go to so-called passivated contact devices. And typically people are also switching from P-type silicon wafers to N-type silicon wafers, because N-type silicon wafers typically have a higher minority carrier diffusion length, which once you reach high efficiencies, then actually it's easier to go even higher with that. So now I will show you 2 examples of passivated contact devices that are already being developed and being produced. The first one still resembles what we have seen before. It's called TOPCon cell, stands for tunnel oxide passivated contact. Was originally developed by Fraunhofer ISE, but there are multiple variations of this developed by different institutes and companies. And now what we see at the rear is actually typically we switch to an N-type silicon wafer instead of P-type, but you can also do it with P-type. And now we have a very thin, this blue layer, a very thin tunnel oxide to passivate the surface. So very thin means it's typically 1 to 1.5 nanometers, because as the name suggests, it's a tunnel oxide. So the carriers need to tunnel through it. So there is some nano technology involved in our large device. And on top of that, then we have a doped polycrystalline layer for lateral conductivity. And then we have, in this case, it's a silver contact on top of that. So now we see we have a device where the metal is nowhere in direct contact with the silicon. And moreover, it's also a carrier selective contact. So it will attract one type of carrier and repel the other type of carrier for extra passivation. And the result of this is that we can go even now again a step higher in the energy conversion efficiency. So at the moment, the record efficiency for this type of device on a large wafer, on a large cell, is 26.7%. So that's quite high. A second alternative example of passivated contact is a so-called heterojunction cell. So this has already been investigated since the late 90s. It's a completely different type of device structure, where actually, again, we have an N-type wafer, but now both surfaces are passivated by very thin layers of intrinsic amorphous silicon. So typically also 6 to 8 nanometers or so. And then we have doped layers on top of that of amorphous silicon or an alternative to have the emitter and the back surface field. Then we have TCO layers, transparent conductive oxides. This is what you need in this type of device because the amorphous silicon is not conductive enough in itself. And then you have the metal contacts. So again, it's a carrier selective device, and you see that the metal is never in direct contact with the silicon. So it's a passivated contact. And also here, around a similar efficiency of 26.8% has recently, or no, let's say 1 year ago, been achieved also on a large device for that. And that's actually at this moment still the world record efficiency for a two-side contacted silicon solar cell. So two-side contacted means you have contacts at the front and at the rear. So if we go back to the roadmap, this means with passivating contacts, we can make a next step upwards, probably in industrial high throughput production going to around 25 or slightly above %. If we want to further increase the efficiency, it becomes more and more difficult because you get more and more fundamental issues. But one issue we can still resolve, that is actually parasitic absorption losses of the light. And this can be done by going to so-called back contact solar cells. So we'll show you one example of a back contact solar cell, the one that has reached the world record efficiency. And so this is a so-called heterojunction IBC cell. So back contact means that we don't have any metal front contact anymore. There is no metal at the front. And the light, of course, falls in from the front. So if you don't have metal at the front, you don't have metal reflection there. So you will have a higher current. But the downside is all your metal of both polarities need to be at the rear. So this is more difficult to achieve. So you see here You have an N-type silicon wafer. So the green areas are the emitter region, and the red areas are the BSF region. And so they are in this interdigitated pattern. So you need, and this is especially tricky for industry, you need to have low-cost processes that allow you to do this patterning. So you cannot use lithography, for instance, what you use in semiconductor is way too expensive. So that's the price you pay. But you can reach very high efficiencies. And actually, a few months ago, a new world record was set by a Chinese company with this type of device. So they achieved an efficiency of 27.1%. We don't know much of the details yet, but this is the current world record for single junction crystalline silicon solar cells. And so typically it combines a very high voltage with a very high current. So that brings us to the next step. So probably in industry, we might be able to reach 26% if we go to these back junction solar cells with passivated contacts. But the problem is then, can we even go further than that? And it's quite difficult because we have to go to a completely different type of device structure. And the reason is, if you calculate, it has been done in the past, the theoretical efficiency limit of a single junction silicon solar cell is only 29.4%. So it's not that high. And we're already at 27.1. We know that you can probably never reach the theoretical limit because there will be always losses. So you have a practical limit, which is probably below 28%. So we are very close to that. Now, if you analyze why is it only 29.4%? Well, we actually, if you have one junction, so this is the case of silicon, we have a lot of the energy of the incoming light that is lost. This curve goes on in normally. So you have part of the light which has too low energy, is not absorbed. But the light that has high enough energy to be absorbed, there also we lose a lot of that energy because of thermalization. And so we only win this red part. So if you do the calculation and you assume that all of this red also is actually leading them to collected electron hole pairs, you get to this 29.4%. But what we can do now is we can go to multi-junction device. A first step is a tandem device. Tandem means you have two things. So you put on top of the silicon cell another solar cell with a higher band gap. And so this will typically be a thin film normally. And this higher band gap, the light will first pass through this higher band gap top cell. So this is the blue part. Because it has a higher band gap, part of the light is not absorbed, but is transmitted, goes to the silicon bottom cell, which is there absorbed. So now if you look to these two things, we basically are using the same part of the spectrum. We still lose all this infrared light here, but we use actually more of the energy in our device. And if you do the calculation, you see that on this plot, this is a sort of a calculation of as a function of what is the band gap of the top cell and the bottom cell, what efficiency you can reach. You see that actually in a tandem device, we go from the 29.4% for the single junction to a theoretical efficiency limit around 44%. So it's a big step up that we take. But you have to combine the right materials with the right band gaps. And the good thing is, if you look to what is the ideal band gap for a bottom cell, silicon is just falling into this range. So silicon is a good candidate. And then for the top cell, there are multiple possibilities. You typically need a band gap of around 1.6 EV. We have the perovskite materials. I will not go into detail there, but it's like a new almost magical material that is being developed and researched for PV by almost everybody in the world at this moment. And there are also other alternatives. Now, you don't only need to have the right band gap, you also, of course, need to have a high efficiency. That's why perovskites are such a good choice. And the light that is not absorbed by the absorber material should actually be able to pass through. So you should have minimal sub-band gap absorption. Now, some results that have been achieved in the last months. So the combination of silicon and perovskite is already working very well. So we have different groups, a company, a research group that are close to 34% with this. So we go from 27 single junction to 34 with this tandem. And of course, you can go even higher if you start using 3-5 materials. which are well proven, which are used, for instance, in space, but they are probably too expensive for terrestrial applications. But so the whole silicon PV industry at the moment is somehow now on this train of, okay, in the future, if we want to continue with our efficiency progress, and this is really needed to further lower the cost, we have to switch at some point to the tandem devices. Now, some other trends I want to quickly point out is, until a couple of years ago, we had for a very long time a standard silicon wafer size, which was around 6-inch square. But in the recent years, we have seen a large variety of different wafer sizes. And at the moment, most of the cells that are made are really on this much bigger wafers. So here you actually see that the largest wafers, this G12, the area is actually 80% larger than what we used to have. So we make now these very large devices. And you see here the prediction of the industry. At the moment already, most people in the industry are using the larger wafers, and the smaller ones are really going completely to disappear. So everybody is switching to the larger wafers because you have a cost advantage. Everything in PV is driven by the cost. If we look to what type of wafers, mono or multi, we also see that actually mono at the moment is completely dominating. So there is almost nobody producing multi-crystalline silicon anymore. Whereas if you go back 10 years, more than half of the market was multi. The reason is we really need to have the high efficiencies to lower the cost at system level. And you simply cannot reach those high efficiencies, is 26% or more on multi. So everybody is doing actually mono. We see that most of the industry at the moment is still doing P-type, but we expect to switch to N-type to the higher efficiency. And then finally here you see the cell technology market share at the moment. So you see almost nobody is producing BSF anymore. That's completely disappearing because, again, efficiency is too low. Everybody is doing PERC, but we already see more and more people starting to produce the passivated contacts, especially TOPCon is expected to get a majority share in the future. But you also see silicon heterojunction, and slowly also you see the IBC. These are really, let's say, the top-notch modules at the moment. For tandems, it will still take more time to have a reliable top cell. Then very quickly, I will go through how now we make these cells into a module. So I have some animation for that. And of course, there are different variations on this, but this is, let's say, a quite old process that is still used by the majority of the cell manufacturers. So we focus here only on the two-side contacted cells. If you have a back contacted cell, of course, you need to do something else. But if you have a two-side contacted cell, so typically you have this finger pattern with bus bars at the front, and at the rear you have a full metallization. So how are now cells interconnected? We use so-called copper ribbons. So this is a copper material, typically a few hundred micrometers thick, a few millimeters wide, that has a coating that makes it solderable, and it's soldered on top of the bus bars of the first cell, and then basically soldered at the rear of the next cell. So that means we connect the front of cell 1 with the rear of cell 2. So we have a series interconnection. The P of one cell is connected to the N of the other cell. And this we can do, of course, for multiple cells. Okay, so then we can look at how is now the module assembly done. So we start actually with the glass material that will be the front of the device. So this is typically 2 or 3 millimeters thick and needs to be as transparent as possible. On top of that glass, an encapsulant sheet is placed. Traditionally, this is EVA, but there are different types of materials being used already today. Then on top of this stack, we place a string, in this case, of 10 interconnected cells in series. So we have seen how the cells are interconnected with this copper string. So these are 10 of these cells in series. And this is the example of the standard 60-cell module. We put 6 of those strings next to each other. So in total, we have 60 cells. Then we actually connect these 6 strings also in series together. So at this point in time, you have one large snake of 60 cells, which are all series interconnected. And these 60 cells are, of course, so chosen that they all have more or less exactly the same current, because otherwise you would have losses. Then we have to put another encapsulant on top of that, but making sure that we can, of course, have the contacts going out. Then there is a backsheet plate, so it's a combination of different layers that will protect the back, for instance, from moisture ingress. And then finally, this whole stack is laminated together so that it's really fixed together. And yeah, then we can put the junction box, which typically also has some of the bypass diodes inside, and we can put a frame around it, typically an aluminum frame. And this is sort of how a standard module has been made for a long time already. Again, there are many variations on this, but this is sort of how it works. Now, because the cell sizes have been increasing, also the module sizes have been increasing. So in the past, typically people were making 60 cell modules, and the cells were 6-inch. So typically you had the standard measure of 1.7 by 1 meter. But at the moment, people are using actually more cells, and the cells are bigger. So you get actually very large modules with 2.4 by 1.3 meter. And at the moment, the main limitation of the size is somehow chosen to just fit into a container for shipment. So that's sort of, at the moment, I think, the limitation that people stick to, because if it doesn't fit in the standard container anymore, you have a problem. You cannot ship it. But because the area is now much larger, that means also and the efficiency is anyway very high of the devices these days. It means also the output power is much higher than it used to be. In the past, if you had a 40-watt module, it was really something very good. But if you now look to the best modules, the highest efficiency modules produced in December, you see there are several modules with a module efficiency of 24%. And because they have a large size, they really have more than 600 or 700 watts. So one module is 700 watts, so it's quite amazing. So now, one thing that I also wanted to point out, although we are making now larger cells, in the end, when they are put into the module, they are cut always at least in two, because the larger you make the cell, the higher the current will be. So all the current needs to be transported. So this leads to resistive losses typically. And by actually, at the end of the process, the cell process, cutting the cell into two, you reduce the current that it will give by half. And this actually gains you several watts. So you see here, actually, everybody in the industry is using either half cell or third cells. So from a cost point of view and throughput point of view, it's better to make the large cells, but once you're going to use them, you should reduce them again in size, because otherwise you lose too much at module level. So it's quite complicated. Okay, so I've given you a brief idea of how the cell and the modules look like and how they are made. Now we can look to the future and see what are some of the challenges we still have. So I told you at the end of 2023, we can say roughly worldwide there is 1.5 terawatt of PV modules installed. So that is a big number. That's very good. But we know that if we want to become climate neutral by 2050, we need to have much more PV installed and also much more wind. So there are different models, of course, that come with different values. But typically, we can say by 2050, we probably need somewhere between 50 to 70 terawatt. And we have only 1.5 at the moment. And it's only 25 years until 2050. So it means we have to further ramp up the production quite a lot. And where today, this is the number for 2022. I don't have the number for 23, but let's say we are around perhaps 400 gigawatts that we are producing per year at the moment and shipping and installing per year. We probably have to go at least a factor of 5 higher in production rate to values of 1 to 3 terawatt production per year. And this is actually very challenging for many reasons, but today I will focus on the sustainability of materials. So we can take the example of PERC. So I've shown you that PERC is at the moment a standard device produced in the industry. It's switching, of course. But if you look to 2021, there was 180 gigawatt of PERC produced in the world. And here you see some of the materials: steel, concrete, glass, aluminium, copper, polysilicon, silver, that is needed to make the systems for 180 gigawatt of PERC. If you look then to the absolute numbers, they are really huge. But then the percentage actually gives you the percentage of this material of the worldwide production that was used. So for most of these, they are still small. But for instance, for silver, you see, we use 2,250 tons, and that corresponds to 8% of the worldwide production of silver. For silicon, it's even more, but of course, silicon can easily be ramped up. But it's nice to see 60% of the polysilicon that was made worldwide was for PV. So clearly, photovoltaics is using much more silicon than, for instance, semiconductor industry already today, which is normal because we make many, many large devices. And in semiconductor, of course, you want to make as many small devices as possible on one wafer. But so now imagine we have to go to 1 terawatt production. So we can just multiply these values by roughly 5 if we would not change anything. And then, of course, these percentages become pretty large. Okay, for polysilicon, yeah, you have more than 100%, but of course, this can be ramped up. But for silver, for instance, we would already need 40% of all the silver. Now, this is not possible because it will also drive up the price and so on. So it already gives an idea. We're talking here about massive numbers of materials that you need. And this is just for PV. You have, of course, the same thing for wind, for batteries, etc. So if we focus just on silver, which is sort of the main limiting factor, okay, if you talk to the industry today, they will say, oh, we have no limits, we don't feel this yet. But it's, of course, coming. At the moment, it's not yet a problem. But here, this comes from a paper where they assume that for each material that we need, and this is just an assumption, of course, an estimation, but I think it makes sense. They assume like we can never use more of a material than 20% of the worldwide production, because this will not be possible. So they limit to 20%. If you limit to 20% of silver that is being produced on a yearly basis, you can calculate if you want to produce 1 terawatt of PV per year, you can allow 6 tons of silver usage per gigawatt that you produce. If you want to go to 3 terawatt per year, of course, you have to divide this by 3. It's only 2. Now here you see for the 3 technologies, PERC, TOPCon, and silicon heterojunction, you see the dark gray is actually the amount that is used today. And the light gray is what's in the pipeline in terms of further improvements on the short term. But you see that all these 3 technologies are still way above the 6 and especially the 2 tons per gigawatt. So that means we really have to drastically further evolve the technology. So you see here also that there is junction. There are 2 reasons for that. One of the reasons is PERC is already further evolved. So there has been put more work into it. But there is also a fundamental reason why TOPCon and silicon heterojunction are higher, because they basically use silver on both sides, whereas PERC you use aluminium at the rear. And moreover, for silicon heterojunction, it's even worse. This is a special type of device with the amorphous silicon layers that cannot stand high temperatures. So if you use screen printing of silver, typically they use silver pastes for that are printed, and then you have to have a high temperature step to fire those pastes. But you cannot do that with the heterojunction because your device cannot stand the high temperatures above 200 degrees. So you need to make special low temperature pastes, but they typically consume even more silver. So what can be done, and that's something, for instance, where Applied Materials, also partner in this project for the photovoltaics, is also active in. They have, of course, a lot of experience in screen printing because they were one of the world-leading companies for screen printers. So screen printing is a standard in the industry, but you see that there's also now alternatives like parallel dispensing and also plating. So you can plate silver, you can also plate, for instance, copper. To reduce silver, we have to have better pastes, and there, for instance, also nanotechnology plays a role. But we can also start mixing it with other materials, for instance, copper, or we can really switch completely to an alternative like copper. Now, copper seems like a logical choice because it's a good conductor also, it's more abundant, but it's a very dangerous material in silicon. It diffuses very fast, and so if you don't take care, it can easily destroy your device. So that's why still some work is ongoing there. So this brings me to the summary then. So we have now worldwide around 1.5 terawatt of PV modules installed. And we see that the world record solar cell efficiencies are getting, for single junction silicon, are above 27% at the moment. So they are getting very close to the practical limit. So that means we, in the near future, have to switch to silicon-based tandems if we want to go further in efficiency and ultimately go above 30%. We by 2050, we don't need the 1.5 terawatt, but we need at least 50, probably 60 or 70 terawatts. So we have to further ramp up. And this will really become very problematic in terms of sustainable production. So I just focused today here on material, on one material, on silver. There are, of course, also issues we have to think about recycling and so on. So there are many more issues, but not enough time to go in detail there. And then, of course, I would like to acknowledge all the people from the Challenges project for the nice collaboration of the last years, and then my colleagues from IMEC and also from other institutes that provided some input for this. And of course, the funding from the EC via the Challenges project. So thank you.
Are there any questions? So it was a really interesting talk, first of all. You talked a lot about we are approaching this theoretical limit, which is really good for the efficiency. However, I don't think you mentioned if we are also getting better in having a long lifetime, because I know as time goes, the efficiency of the cells typically go down. But are we also improving on this area? Are we just improving the, now you buy this, it's really good now, and then it will degrade within a very short time compared to the older model?
Yeah, no, that's a very relevant question. So the question is about, do we also improve next to the efficiency also in other things like lifetime? So yeah, in general, I think that's what we now see. Lifetime is one element, but in general, I would say we should talk about energy yield. So the efficiency is, of course, something that can be easily measured, but this doesn't say much because it's measured under standard conditions, which you almost never have during the operational lifetime. So, and up to now, what industry mostly did was producing the same type of panels and using it for everything and everywhere. Now we see, because the market is now so big, it's also possible to do it. We see more and more diversification. So it means if you're going to install a panel in Belgium, for instance, where I live, or you're going to install it somewhere in Morocco, it will have completely different temperatures, different climate. Perhaps in the desert, you will have sand and so on. So if you would use the same panel, the energy yield that it will have will be completely different, and also the lifetime will be completely different. So for energy yield and lifetime, you really have to tune the module and the materials you use to the application and the climate that you're going to use it. And this is actually also something that is starting to be done. So yes, when you buy a PV panel, talking about a lifetime, for instance, you will get a warranty of at least 20 or 25 years. But you have to still be careful with this because, it really needs to be tuned to the location where you use it. But we are also improving a lot on that. So it's not just about efficiency. Efficiency is, of course, always nice as a show-off, but there is a lot of other stuff behind that to improve the energy yield, because in the end, it's about how many kilowatt hours you get out of your system and not about the efficiency. For lifetime, I think people are also trying to go to beyond 30 years, let's say. But again, it really depends on the climate and especially the temperature. If your module sees higher temperature, it will typically degrade faster. And so if we know that we're going to use something where it's very hot, then we have to start using different materials to tune for that.
the design of the solar cell is also affected for future recycling processes?
Yeah, so that's a good point. So I didn't go into that. Okay, so yeah, sorry. The question is the design of the solar cells also optimized for recycling? So at the moment, it's not. Well, the design of the solar cell is one thing, but is the main problem is in the module. So of course, we laminate everything together in such a way with the goal that there will not be any moisture ingress, nothing can happen, so that we have a very high lifetime. But this is, of course, bad then for recycling when you have to take everything apart. There are already some companies that produce modules with a different type of technology, for instance, with a kind of vacuum sealing and so on, that should be easier to dismantle. But in general, this is one field where still a lot of work is needed, where we have to rethink how we are actually making these modules so that at the end of life, they can actually be recycled better. So at the moment, also the standard technology, it can be recycled, but it comes at a high cost. So the recycled material at the moment that comes out of the recycled modules is typically much more expensive than the raw materials. So at the moment, there is no business case, let's say, no good business case. The only reason that we do it now is, of course, because of environmental reasons. But in the future, if we can make it easier to dismantle, but also when the raw materials will become much more costly because we need a lot of them, not just for PV, but for all the other renewable technologies, also the business case will automatically also become better. Now, most of these materials that come out of the ground are still too cheap, let's say, for people to really care too much. But yeah, the good thing is, of course, also in Europe, for instance, in most countries in Europe, especially here in France, Germany, and Belgium, and so on, you already have these take-back schemes. So PV is considered as an electronic equipment. So whenever you buy your modules, you have to pay a few euros extra, and this money is used at the end of life to collect them again and so on, and to make sure they're not just dumped somewhere. But from collecting them to then having actually economically making sense way of recycling them and reusing then all the materials, that's still something else, of course.
So if there are no other questions, thank you again, Ivan. Hello, everyone. We can start again. And we have a presentation from Amaya. And she's here. So
yeah, hello.
Thank you, Amaya. You have 40 minutes. The floor is yours.
Perfect. I will start by sharing my screen.
We can see your screen.
Okay, perfect. Yeah, sorry, I had to give permission. Okay, so I hope it's on presentation mode now. Can you see?
Yes, we
Okay.
confirm it's on presentation mode. Thank you.
Okay, thank you. Thank you. Hello, good morning, everybody. Thank you, Marta, for the introduction and for the invitation to give a presentation in this second Challenges training school. Unfortunately, yeah, I cannot be there due to other commitments, but yeah, I have the opportunity to show you some of our work and share it with you. So the title of my talk is Process Control and Quality Control on Graphene. I will briefly introduce Graphenea. So we are an SME, small medium enterprise company. I mean, we are not a startup anymore. Usually after 5 years, the company is not a startup, and we started in 2010, so 14 years ago. So we stopped being a startup company many years ago. We are based in San Sebastian in the north of Spain, and we are based in this Miramon Technology Park. This is a photograph. We have 2 business units in Graphenea. On one hand, we have Graphenea Advanced Materials that deals with graphene oxide and graphene oxide derivatives. We now have a spin-off company that will commercialize this more for industrial additives in the chemical industry, a spin-off called Kiboro. that we started last year. But today I'm going to focus on CVD graphene, and because this graphene is more suitable for, let's say, for the semiconductor industry, for optoelectronics and photonic type of applications, also sensors. So I'm going to focus on graphene semiconductor, on the work we do under the graphene semiconductor umbrella. We are around 40 people, I think 42 people. As I said, we started in 2010, so a long time ago. We produce most of the graphene materials in our headquarters building in San Sebastián, but for the chip production, we use a nanotechnology research center called CIC Nanogune. So our graphene devices are manufactured there. And then we have a sales office in the US, in Boston, Massachusetts, Cambridge. And this is a world map where you see how much graphene we sell. So at the moment, we are selling especially the CVD graphene for research. It's at research stage. We have supplied to more than 60 countries. I think we have more than 800 customers worldwide. And of course, the blue circle, the larger the circle, the more graphene we sell in that area, in that geographical area. Okay, so a bit more on future plans of graphene semiconductor. Here you can see a photograph of the present. I mean, this is when we opened the clean room a few years ago. Now it's more busy with equipment. But I wanted to share with you a bit that we will be moving to a new building where we will have a much larger clean room. The building is currently being built. It's a bit more advanced than what you can see in this photograph. But there we want to have our own chip production facility. So a facility where we can produce graphene field effect transistors at 200 millimeter wafer scales. And we will be moving there in a couple of years' time, hopefully. Okay, so now I move to the outline of my talk. So I want to tell you a bit about graphene fabrication of this CVD graphene, and then how important is the quality control at wafer scale. And also the difficulties that we encounter because we are dealing with a bidimensional material. The third part I want to tell you about a bit is about how to integrate this graphene in industry and show you an example of photonic integration where we collaborated with IMEC in the framework of the graphene flagship that finished last year. And I will finish off with some conclusions. Okay, so a bit on, I wanted to cover briefly here some challenges we have in the technology development of this material. So the first challenge is that you have to work at the right wafer scale. So most, let's say, silicon transistors are manufactured on 300 millimeters. But for example, the most sensors that are used in mobile phones are fabricated on 200 millimeter wafer scale. So you need to get that right. So with graphene, for the growth up transfer, we are at 200 millimeter wafer scale. So we have a relevant industrial scale for producing the material. You want to have a decent process rate, scalability. Of course, you want the graphene to be homogeneous, growth reproducible, not only growth, of course, also the transfer. And then related more to the integration, well, you want the graphene surface to be very clean, also to have a controlled metal contamination present on the layer and as low as possible. Of course, particle count is also quite relevant for the semiconductor industry. And of course, you want this at a high yield. So things get complicated. And these are some of the challenges that we face. Another point here is about the quality definition. I mean, most applications, you need mobility, so a high mobility for the graphene. But this mobility value can vary depending on the application. So some applications require higher mobility, others lower. And this, in a way, is good because you try to achieve the lower and then you go increasing that mobility. And finally, the quality control, which is the main part of the talk, that to have relevant QC methods at wafer scale is very important. Yeah. So in order to move from the lab to the market, I already said we need industrially relevant wafer scale, and we have to do everything at wafer scale. So the growth, the transfer, but also the device fabrication. See, because most of the applications will require the fabrication of graphene transistors, different types, but of graphene transistors. And of course, at each step of, let's say, after growth, after transfer, we need to develop the right quality control there. Okay, so a bit on the growth, how we do this growth. So this is a photograph of our CVD reactor. Is only a thermal CVD that we do. You can see this a photograph of our actual frame that goes in the reactor. So this is 200 by 200 millimeter. We use copper foil as the catalyst, and we expose it to 1000 degrees. I said it's thermal CVD. And then we inject methane as the carbon source. And with methane, you start getting nucleation points, and then the graphene grains grow. And then finally, when these grains merge, we complete the film, the graphene film. And it covers the whole surface of the catalyst layer. So this graphene is polycrystalline. It's not like silicon that is a single crystal. In this case, it's polycrystalline. But still, with this polycrystalline graphene, we get pretty good mobility values. As I will show you later on. There are some other options for CVD reactors out there. So you could use a tube furnace to grow graphene. Roll-to-roll systems have also been reported, or an MOCVD type of system for growing graphene. Okay, so a bit on the evolution of the growth of graphene on top of copper foil. So of course, I said that we've been around for 14 years, but yeah, we have experienced an evolution on the size, especially. So initially, we were growing very small 1 by 1 centimeter copper foil pieces. We were introducing them in the reactor and growing graphene. Then we moved to 4 inches, then to 6, and now we are on 200 by 200 millimeters. Some of the aspects that we need to take into account and try to control, so to have homogeneity across the full copper foil. We want the runs to be reproducible, all the time the same. Of course, we have defined what is a batch, and could be a few foils, and then the next batch in order to do a quality control there. Some challenges related to growth. So one of the challenges is the multi-layer graphene areas. What does this mean? So typically in the nucleation points, not always, but sometimes you have a bilayer graphene growth there. So you want to have as low as possible these multi-layer areas. The roughness of the foil is also a challenge. Of course, by definition, a foil can be quite rough. There are different catalysts that you can also work on, like thin film, copper films, deposited on sapphire, and there you decrease the roughness quite a lot. Because at the end, the rougher the surface of the foil, well, graphene is going to follow that surface. So it could end up with more wrinkles and other issues. And another challenge and parameter that you can change is also the crystal orientation of that foil. That typically the one we use is polycrystalline, but if you have a single crystal like copper 111, then you can also improve the quality of that graphene. So in the research department, we are working, of course, on improving our existing copper foils, decreasing the roughness, also working on these thin films deposited over rigid substrates like sapphire. But today I'm going to talk about the material that we have more in production, which is the one grown on copper foil. For ensuring growth homogeneity, we do Raman. I mean, these are results after transfer, but we can also do on the copper foil using a blue laser. And typically we analyze different areas, so center, top, bottom, left and right. We map different areas there, and then we extract the relevant data. So we do a lot this type of stress strain doping curves, and of course you want your film to be as close to the zero doping and zero strain there. But as a consequence of the transfer, you typically have a certain strain and doping. We also follow different parameters. So, for example, the position of the 2D peak, the position of the G peak, the full width and half maximum of the G and the 2D, but also the intensity ratios of D, which is the defect peak, over the G peak, and the G over the 2D peak. So all these parameters can tell you about the homogeneity and also the quality of the graphene that you have. So we use Raman quite a lot. A bit on the evolution of the transfer, so similar to the growth step, also the transfer of graphene has experienced an evolution. So at the beginning, we were doing transfer at coupon level, so 1 by 1 centimeter. Then we moved to 4 inches, 6, and then we went to 8. So this is an 8-inch silicon wafer where we have transferred an 8-inch polycrystalline graphene film there. And we can, of course, also transfer graphene onto 300 millimeter wafers. So I'm not sure if you can see, this is the edge of the film, because it's, yeah, of course, it's smaller than the wafer. We transfer using a semi-dry transfer that relies on a flexible polymer carrier. Some of the key aspects for the transfer process. So you want to have, of course, a low defect density. You want the graphene interfaces, the top and also the bottom, so between graphene and the substrate and on top of the graphene, to be as clean as possible, free of metal contaminants, polymeric contamination. You want the graphene to be very flat and ideally to have low strain for the applications. Challenges, similar to growth, homogeneity, reproducibility is a challenge. In the transfer process, I would say that addition is probably the biggest challenge at the moment. And I will show you some examples of bad addition, what happens. At the end, the graphene breaks and you need to optimize the transfer process to improve that addition. And all the wafers, every wafer is different, especially if you have a pre-patterned wafer. So you need to optimize the process every time, yeah. Metal contamination, to control this metal contamination is difficult. And ideally, you want to have the process fully automated in order to remove operator variations there. The good thing is for the transfer, we use semiconductor industry tools. So we use tools that are already used in the industry. So this is good. I mean, this decreases the entry barrier in terms of equipment cost. If you have to develop a new tool only for graphene, yeah, this is going to be more complicated, and also the time you need is much longer. Okay, in principle, we could transfer graphene onto any substrate. And so far, we have not found a substrate where we could not transfer graphene. Of course, I said there is this optimization needed when you change the wafer type. So we can transfer onto coupons, pre-patterned coupons, flat wafers, even easier, of course, 300 millimeter wafers. Here you see much better the 200 millimeter graphene. the 300 millimeter wafer. This wafer had waveguides, so yeah, you just transfer on top, and we can even suspend graphene. So this is a cavity, and here you can see a graphene wrinkle, but graphene is fully suspended there. Yeah. So in principle, the transfer process is quite versatile. Okay, now moving to the quality control. So we use different methods to qualify the graphene wafer, let's say. Of course, this industry, the graphene industry, is quite QC intensive at the moment, because once you have the processes really established and fully under control, you want to minimize the QC, but at the moment it's quite QC hungry, I would say. So we use optical microscopy, Raman. I will also talk about AFM, and finally about the electrical measurements after device fabrication. And we also use other complementary methods like SEM, XPS, TEM, TXRF. This is for measuring metal contamination, and TOF-SIMS is also for contamination. So at the end, you need to use a lot of different techniques to know exactly what you have on the wafer. Okay, so this is these are some heat maps of all the optical microscopy images. So we have developed a code, an optical microscopy image analysis code, where we have defined some defects. And for us, a defect can be a hole, can be a residue, can be particles. So we can analyze, this is done automatically. We put the wafer in our optical microscope, and it does the full wafer inspection, and we get this type of heat maps. And of course, we have set some limits to qualify the wafer. So if our heat maps are worse than our limit, then we can discard, or let's say we reject that wafer. So it's a way of qualifying wafers. For the devices, we also use optical microscopy. Here you can see a graphene channel that has no defects. Of course, what our image analysis does is it colors these defects, and that's how we determine the area that we have of the different defects. And we use this also to qualify the different chips that we produce, or wafers, depending. Sometimes we sell the individual chips, but we can also sell full wafers to customers via our graphene foundry service. For optical microscopy, we think it's quite versatile. You can even go even farther. So by changing from bright field to dark field, you can really enhance the contamination that you can have there. So many times, I guess you know, but graphene, depending on the substrate that you have, the contrast can be good or bad. You could have almost no contrast. So in those cases, we need to rely on the dark field mode in order to enhance the defects. Optical microscopy can also be used for counting multi-layer areas or even wrinkles. So it's quite a versatile tool that we use quite a lot. Now moving to Raman spectroscopy, I said we can also do a Raman on top of the copper foil, just after growing the graphene by using a blue laser. And then on the transfer, we use green, and after device fabrication, we also use the green laser. This is a plot after the transfer, and this after device fabrication. So I said we want to be as close as possible to the low doping, low strain cross there. For the AFM, we also get quite a lot of data. So it is not so much quantitative, but we use it for qualitative analysis. Of course, the difficulty with the AFM is if you have a 200 millimeter wafer, I mean, we can analyze some areas, but still it's a very small percentage of the full wafer. So that's why we say it's more for qualitative, but it gives us a lot of information, especially on how flat our graphene is, if we have particles, the presence of particles, the distribution of the wrinkles, and last but not least, about the polymer contamination that we have. I said we rely on a flexible polymer carrier for the transfer, and this leaves some residues on graphene. So with AFN, we can see how clean that graphene is. And we do this after transfer and also after device fabrication. So one of the issues of device fabrication is that you use photoresists, and this also leaves a residue on graphene. So we developed a method for opening a window, and then we measure the step height, and with that we can estimate more or less how much polymer we have there, if we need to apply extra cleanings and so on. Yeah. So it's quite a useful tool also, although the wafer scale characterization is a bit open. And of course, we do also different, so 25 by 25 micrometer window, 10 by 10, and 2 by 2. And each one of them gives us useful information. For the electrical measurements, okay, for this we need to fabricate graphene field effect transistors, but from a wafer, I mean, we have some chips that are for quality control, and we can extract quite a lot of data. So here you can see a typical wafer where we get around 2,300 centimeters square volt per second of hole mobility on our graphene chips. I said we sell chips or full wafers. We also have this is a 1 by 1 centimeter chip for biosensing applications. So this is designed for working in liquid environments. But we also sell smaller chips, and these are of course cheaper. This is a 4 by 4 millimeter for the same application for biosensing or gas sensing. They could also work. Yeah. Okay, and now for the final part of my talk, I want to talk about the integration of graphene for photonic applications, for example. And in this case, well, this was the result of quite a few years of work in collaboration with IMEC in the framework of the graphene flagship that finished last September. And here, we wanted to show that graphene, well, CVD graphene, could be processed in IMEC's 300 millimeter CMOS pilot line. And this is, let's say, a milestone to demonstrate that it can be processed in an existing, let's say, using industrially relevant processes. And we fabricated single-layer graphene electro-absorption modulators. It was a fully compatible CMOS integration process that was used, CMOS integration technology. We introduced graphene in IMEC's pilot line that we had some challenges, especially related to the presence of metal contamination, that they have quite a strict requirements there. And then for the contacting of graphene, we use the Damascene approach for introducing these tungsten-based contacts. And this is to enable the CMOS compatible integration. And this was done successfully. And then at the same time, we did a design experiment to check different factors affecting the processing of graphene. And of course, this is a path for large-scale manufacturing of graphene devices. Yeah. Okay, so briefly, what was the process flow and what parameters we studied? So we checked the surface flatness before the graphene transfer. So you can see how we transfer graphene in this second step. Then we also studied how to do the encapsulation of graphene. And I will show you in the next slides. And the final parameter we checked was the time of contacting. So from the via opening to the via filling, how much time we left in between. For more information, of course, you can check the paper there. Okay, so I briefly mentioned about issues with addition. So this is what happens if the transfer is not optimized for obtaining good addition. So you see here, we have pieces where there is no graphene. So this wafer is useless. And we had to optimize the transfer. And after optimization, we got very good addition. So yeah, we were quite happy about that. But it took quite a few iterations, yeah. And of course, these wafers are very expensive. So yeah, we worked on dummy wafers first. Okay, so for the 3 parameters that we investigated, one was the surface roughness. So we compared 2 different surfaces, 3 nanometers versus 0.4 nanometers. And the lower roughness was obtained using an extra chemical-mechanical polishing step. And then, of course, we saw the performance of the modulator. But you will see that here how I mean, the best results were obtained with a much smoother surface than with the rough one. For the second parameter, this was the encapsulation. So there was a soaking method was used, and we determined we compared a short soaking time versus a long soaking time. And the best results were obtained with a long soaking time. In fact, you can see that the encapsulation was not, the layer was not full if we used short soaking times. So it was not fully passivated, the graphene there. And then the final parameter that we checked was the time delay between the via opening and the filling of the contacts. And we saw that if you let's say, from the re-etching of the edge contacts to the graphene to the filling with the metal a long time, yeah, it was not good. So we determined that it had to be done straight away after the etching. Okay, so these are the 4 wafers that we processed in IMEX pilot line. And I already said what the best results we got with wafer D, which is the one with the extra CMP, so very low roughness substrate, long soaking time, and no delay between the etching and the metal filling. Okay, and now moving to the final part, I wanted to show you some figures about market values for graphene. I mean, it has not been easy because, I mean, there are a lot of market studies published, but some, they either provide very high numbers or very low. So I took one that was in between. And I selected this one because I like this split in terms of applications. So you can see that electronics, I guess this also includes photonics, sensors, biosensors, and so on. So the market is expected to evolve, and electronics will have a relatively decent market for graphene. And it is expected to grow to $3 billion by 2030. And just to finish off, I wanted to also say that at the end, new advanced materials need a lot of time to hit the market or for them to be widespread in products, in commercially available products. So the silicon industry took many years to be the market we have today, right? That moves a lot of money. The first transistor was discovered in 1947, and it was not even made of silicon, it was made of germanium. Same for carbon fiber. The aerospace industry, I mean, now every plane has a carbon fiber, but and they have managed to consume less fuel, and they are much more efficient now, but this took many more than 20 years. And anyway, there are some other examples here the fluorescent lamp, the liquid crystals, Kevlar, PVC, polyethylene in packaging. I mean, they all took quite a few years. And final slide, conclusions. The wafer scale manufacturing processes, including QC, are critical for successful integration of graphene in industry. Scalability of graphene growth and transfer is possible. We also demonstrated the CMOS compatible integration in collaboration with IMEC. Okay, the modulation depth of the photodetect of the modulators, electro-optical modulators, was not so impressive because there are still some other wafers that we are investigating at the moment, and one of them is that you need to use, let's say, a double single-layer graphene. So we stopped in the middle. So now we are working on adding a second layer and an oxide in between in order to improve the performance of those modulators. But anyhow, even on this first study, I mean, we measured 400 devices, so this gives you quite good statistics at wafer level. Yeah. And the final point would be that, and positive, the integration of CVD graphene has many challenges, but they can be overcome. And we expect that there will be applications hitting the market hopefully soon. Still, they will take a few years, but yeah. Okay, and yeah, and that's it. I thank you all for your attention.
Okay. Thank you, Amaya. Are there any questions? Yeah. Can you come here so she can hear you?
Yeah, just a short question. Is Raman used inline, online, or offline?
Offline.
Yeah.
At the moment, offline. I mean, of course, we would like to use it inline, but at the moment, it's not even automated. So we have to move manually and, yeah, using knobs, so it's not there yet.
And also the case regarding XPS?
And XPS is not, I mean, of course, in the XPS, you cannot fit a full wafer. So you need to dice it. So XPS, I would say, is destructive for the wafer. So we do XPS on the batch analysis. And also SEM is also the same case. I mean, we don't use wafer level SEM. We don't have it. Yeah.
Do you also focus on fabricating epitaxial graphene on silicon carbide? Because last publications have shown some efforts producing semiconductor buffer layer on silicon carbide, shown by Van der Heer et al. Do you think that has some impact for the production?
So to be honest, we have not grown graphene on silicon carbide. The temperatures you require are much higher. And then also the transfer is very complicated. So to transfer from silicon carbide to another substrate is not straightforward. While if you grow on graphene, you can transfer it. Of course, it's not the graphene we produce is a semi-metal, is not a semiconductor. So that's why we are not targeting digital applications. It's more as a modulator, or let's say in the biosensors or sensors, or targeting different applications.
Thank you.
Thank you.
Are there any other questions? No? Okay. So thank you again, Amaya.
Thank you.
Let's go on with Irio. To say this?
Yes. Questo dove avanti e indietro, questo è il puntatore?
Invece il puntatore, sì, ma qui no, vai avanti e indietro con le freccine.
Con le freccine. Okay.
Un attimo solo che condivido lo schermo.
Okay.
Good morning, everyone. I'm Irio Lavagno from Tiberlab. I'm a software developer, so amongst engineers and physicists, I'm quite the outlier, but I will try to not to ruin your p-value. What I gathered from your previous talk is that you all generate lots of data. So you probably need some way to store your data in an efficient way. And more than that, you probably need some way to retrieve your data in a meaningful and reliable way. And even more than that, maybe you need to query your data or your metadata. So have a way to retrieve your data using some criteria, which gives you an ordered, sorted or filtered way to retrieve your data. So I guess some of you or many of you are already using HDF5. I don't know if you are familiar with it. HDF5 is the name means hierarchical data format, is a storage system. It's substantially is a data format and plus a few libraries to access the data itself, and a few tools built on those libraries. It has many advantages. Among those, it's open source, it's cross-platform. It stores data on a single file, so it's easy to share, easy to backup, easy to move. It's fast, allows to store metadata along with data. There are libraries for it in many programming languages, so it's easy to use without learning different programming languages. And one interesting thing is that it has a tree-like structure, so it's sort of structured like a file system, where you can imagine the nodes of the tree are like directories, and the leaves are the data sets, which are like files in a file system. I will come back to this file system thing later. So the structure of the data in the HDF5 is substantially multi-dimensional vectors of data, where the single cell can be either and 32-bit integer, 64-bit integer, floating point, or whatever. Associated with it, there are metadata, which are some structural metadata, like the ones you are seeing, like the ranks, so the dimension of the matrix, and the data type, some other attributes, etc. And you can add your own custom metadata, so you can add things like, for example, the instrument with which you have made the measure, the setup of the instrument, calibration, the institute doing the measure, and so on and so forth. What HDF5 is missing is that the associated metadata can be queried, but in a very, very simple way. You can just the metadata substantially are a key value map. You can do query by getting single values, like the value for a single parameter, or maybe for more, but just in a very, very, very simple way. So we used a feature of HDF5, which is that it's very modular and allows for plugins to be created that intercept some of the flow of the operations, and allows you to replace it or just enhance it if you want. In particular, we use the VOL plugin, which intercepted the layer when between where the data are inserted and the process that brings them into the database, the data store. And we replaced the metadata storage with a SQL database. This allows for more complex queries of the metadata, aggregations, sorting, filtering, and so on and so forth. We choose SQLite because it's also allows for storage in a single file. It's very lightweight, very fast, actually. It's optimized for different environments, so it's quite a good choice for this. In the expansion, we will see that we are also thinking of using more complex databases. So what happens here is that when you insert your data into the system, the metadata gets stored in the SQLite file. And when this allows with a further, I don't think I need to explain what SQL allows. Anyway, it's a relational database, so it allows aggregation of data, multi-table association, complex queries, and so on. No, this is later. So after you store the data into the database, you can do queries using additional APIs that allow you to retrieve your data doing complex queries. Going back to the fact that HDF5 is structured as a file system, what I thought is to actually create a virtual file system, which is available on many operating systems. In this case, it's on Linux, but it's also possible on Windows. That is integrated with the plugin, so it allows you to drop a file into a directory and have it automatically processed within the system to extract data and metadata and store them into the system. This allows you to take a file that comes from an instrument, just copy it into the system without thinking about what file it is and so on, and have it automatically inserted into the database. This phase also allows for pre-processing of the file. I forgot to make a slide about it. The pre-processing also is pluggable, so you can write different plugins in our system to actually process the data, especially the metadata, and normalize them. So we were trying to make the system able to harmonize the metadata that come from different instruments and have different names to homogenize them and have them stored with the same structure according with the. We try to follow the Charisma guidelines. The system, since now we have a virtual file system, we can also use to interrogate the system. So it automatically generates a virtual JSON file. I think you're familiar with JSON, with the JSON format. If not, I can explain what it is. I don't know. Anyway, it's a simple data format which allows for key values expressed in that format. You have a parenthesis that specifies a block, and then a series of key value items. Where the value can itself be another structure, so it's also again a tree-like structure. You can have also vectors or other kinds of structure. It also generates automatically a virtual JSON file, which allows you to see all the metadata without having to use any APIs or anything. You just can show it or copy it outside of the system and use it somewhere. Another part of the system offers a REST API. So it's an API that you can use over HTTP. So it can be queried programmatically, even remotely. This allows for programmatic access to the structure. You can write your own program and query the data and so on. And okay, I already talked about this. The REST API also offers a standard interface and well-documented interface to the system. You can access everywhere, even securely with the HTTPS. And also there's a layer of authentication authorization, so different person can see parts of the data and not everything. So you can divide the possible access to the data. There is also an example web app that allows you to access the data that uses the REST API. The web app is, at the moment is very rough. It is just a proof of concept, and it's quite ugly. But so I didn't put any image of it here. And so the overview of the system. This is mostly how it is in overview. So you have I can't see anything. So this is what I told earlier. It's just I don't know if there's something more to say, but I don't think so. And there are future possible enhancements which are in our wish list. Other SQL engines like Postgres or other databases that allow a more advanced access to the data compared to SQLite. It's much better. Yeah, thanks. Add a decent web interface compared to the one that we already have. Add more parsers, preprocessors. So far, we only are able to parse WDF files from WITEC. because most of the data files that come from the instruments are proprietary formats, and most of them are not documented. So they either need either to be reverse engineered or contact the manufacturer and hopefully get the specific specifications of the formats. There are already some public libraries that allow parsing of some of the data files, so we think to integrate those in the system. Add also querying and sorting on data, not just on metadata, and also maybe aggregation on the data that could be probably useful. Though that part is very complex because you need a SQL parser going to access the data. It's not very easy to build. And also add something like vector databases and LLM interface, which is a buzzword at the moment, to be able to query data maybe even in a more in an easier way, like natural language query or something like that. And also thinking of the previous talk about machine learning, maybe HDF5 could be a nice way to provide data to the machine learning to have all the data stored in the system, and then provide the data in an efficient way to the machine learning systems. So that's all. Probably I've been very quick, but that's all. So thank you. Just another thing: the code of the whole system will be put on GitHub in the next months. So it will be available to everyone if someone wants to either use it to do something else or improve it, collaborate with the project. So thank you.
Hi everyone, and welcome back. So we can start this final session and with the presentation of Vittorio. And let me give you the floor. Thank you.
Okay, thank you very much. Good afternoon. So this last lecture will be on TM on graphene and 2D materials. So Roberto told yesterday that I would have give you a more detailed description on TM working principle, but it's not true in the end. Because actually, I mean, yeah, you are definitely a liar. And so, because he gave already, I mean, an overview of how the instruments works, and it's, I think, a little bit far from the scope of the school to go too much into the details of the instrument. So we'll focus mainly on what can be done onto the materials. So let's start from this picture here. So you see the three big families of microscopes. I mean, in terms of analogy between optical microscope and the transmission and scanning electron microscope. Just keep in mind that essentially, I mean, it will be the TM, the real and the only counterpart of the light microscope, because you have electrons in place of light, and you have electromagnetic lenses in place of optical lenses in order to, I mean, focus the electron beam, pass it through the samples, and then having additional optical system after the sample in order to obtain an image. The SEM, that is pretty similar in the end, it's completely a different type of instruments. We have no time to discuss about SEM today, but keep in mind that this is not a real microscope. Actually, it's just a sequential forming machine with a beam that is scanning over the sample, and then each point will modulate the intensity on the screen and form the images by point. And we will see that there is a sort of hybrid approach where this kind of instrument here can be used also in this modality. I mean, in just scanning the beam over the sample. From a Venn point of view, why TM or SEM? Because it's always a matter of dimension. So here you see just a scale, a graph showing, I mean, the size of the different things that you would like to see. And up to a certain dimension that is around 100 microns, something like that, A's are enough. So you can just use your eyes to see what you see. But then, I mean, if you have to go down, you have a large region when you can just use SEM or light microscopes. But if you want to go down to very small things, in particular, I mean, on the size of the atoms, then the only chance is to use TM. And so this is one of the reasons why this instrument is so powerful, even as we perfectly know, it's definitely not online and completely destructive. So that's what we said. So here it's a functional scheme of the instruments. As we said, we have on the top the source of the radiation that you use. In the case of SEM, of electron microscopy are electrons. Then you have electromagnetic lenses, essential electromagnetic lenses with a circular symmetry with are capable to work as lenses, means to bring all the electrons that are coming out from a point and to focus them in the same point in the imaging plane. So that is the general definition of a lens. Here in the middle, you have the sample. So here you see the scheme of the lenses. And here you see a sort of open column to see how it works. So these are the lenses actually in terms of electromagnetic lenses. So there are, I mean, wires where they're capable to produce a very intense field just along the optical axis. And here you have the sample. This is typically in the middle of the objective lens. And from the functional point of view, you have the first part of the lenses that act as a transport mechanism for the electrons towards the samples and to reduce the probe down to the samples. And the second part of the lenses, that is the so-called projection system, that is the one that brings the image that is formed in the backfocal plane of the projective lens and bring them to the final screen. The core of your instrument is definitely the objective lens, where you have the higher field, and it's the lens that gives the quality of your instruments. Why? I mean, if from the functional point of view, there is an analogy in terms of how the instruments works. From the point of view of the contrast formation, so the mechanism is completely different, because essentially in electron microscope, you have electrons that are passing through the materials and are interacting with the structure of your materials, and there is no, or at least it's not really fundamental, the absorption of the electrons within your materials. So you have definitely, in general, three types of contrast. One is the so-called mass thickness contrast, that is essentially related to the elastic scattering of electrons by atoms, and to some extent can be considered directly dependent on the atomic number and the density, and also the so-called density and composition, so the mass, so-called mass thickness of your sample. Then you have diffraction contrast. Diffraction contrast is similar to mass thickness, but is related to the interaction of the electrons with ordered structure inside your instruments. So you have this, what already Roberto was describing yesterday. So you have ordered scattering along specific directions that are related to the structure you have in your sample. And so this gives you information about the crystallographic domains and the structure within your system. And then you have finally the so-called phase contrast, that is again related to diffraction, but is actually related to the interference of a diffracted beam. And this is what it's the source of what you call high resolution images, actually. That is one of the things that we will discuss today. What makes the TM so powerful is actually the capability to have always in the same instruments both the information related to diffraction and both the information related to images available to the observer. Because just depending on the excitation that you put in your lenses, you can bring what is formed in the backfocal plane of the objective lens on the screen, And in that case, you have diffraction and you are working in so-called diffraction mode. While, I mean, on the other side, when you excite the lenses in a different way, you can just take with the projection system what happens in the front focal plane of the objective lens and bring it down to the screen. And in that case, you have imaging. So both this type of information are always available. And this is what makes, I mean, your instruments powerful, because you can at the same time have imaging information and information about the structure. So when we are talking about the diffraction, it's a phenomenon, a very general phenomenon that appears when, I mean, a wavefront essentially interacts with an obstacle or a discontinuity in the medium which is propagating in. And here you see the here you see the diffraction from light passing through a hole, or waves passing through a discontinuity in the medium. And ce n'è un altro. Codesto? And when we are talking about material, what is interesting is that from diffraction, so Roberto yesterday was discussing about the use of diffraction just to map strain, but from a general point of view, you can achieve information about the ordering inside your structure. So here you see just 3 examples of a diffraction pattern coming from an amorphous material, so without ordering structure inside, or to some extent with an order of the very, very short distances, or a purely single crystal or crystalline material, but also to a sort of polycrystalline material. So based on the type of diffraction pattern that you have, you can just discriminate between the different type of ordered structure that you have within your material. And also, and this is something that we will see for graphene actually, you can also some additional features that are related to the superposition of diffraction pattern from crystalline structure, giving rise to some superlattice structure that can appear when you're just observing directly, I mean, the structure of your materials. And from diffraction, you can obtain a large set of information. Actually, the diffraction allows you to distinguish between crystalline to amorphous materials, check the properties of the crystal, so measure the lattice parameters of the symmetries or the order inside your system or whatever, analyze the polycrystalline properties in terms of grain size and morphology, dimension, distribution, etc., phases, crystal orientation, but also, I mean, characterization of extended lattice defects. It's not really the case of graphene, but was really one of the main application when we were studying, I mean, semiconducting materials also in the last years. So starting to look what you can do with this kind of capabilities to graphene. So here you see the 2 main ways you can just prepare a graphene sample. So normally you heard this morning from Amaya transfer method based on CVD or in generally grown 2D materials. Here is the typical method you can use. Essentially means that you start from the film on the growth growth substrate, and you have some chemical methods. This is the lab-based, the classical method that has been used for years. Then Amaya show you that if you have to move towards industrialization of the process, you have to deal with something different, but this is working properly if you have just to characterize the materials in the lab. So you have just, you see here, are pieces of copper with graphene on top that are put in an acid solution. The acid solution will be dissolved by the metal will be dissolved by the acid, and what you end up to have is just the layer of graphene with a polymer support on the top that is just floating on the top of your acid solution, and then you can just drop cast it. You can just scope it with a grid and having the film on the top of the grid. On the other side, you know that with graphene, that is not a matter of challenges, but this is what it happens in the, production of those materials. Another way of producing materials is by chemical methods. So you have typical inks, so solution in different media having graphene platelets or flakes inside. And what you can do easily is just to drop cast the solution on the copper grid, and you just observe what you obtain. And this is our first example of what you can do with TM, with graphene. So the first information that you can achieve is about the morphology. So from just observing, these are flakes was one study of, the different techniques of exfoliating materials in some solvents, and just observing the morphology, you can just obtain several types of information in terms of the dimension of the flakes, the folded edge, the layers were just due to the contrast that you can observe, you can just see where you have superimposed layers and so on and so forth. So essentially, what you can obtain from few graphene crystal layers, obtain information about the shape or the stacking, the morphology, the scrolling that you see in this region here, and so on and so forth. But then you can also use TM to analyze, the capability of functionalization. Here you see again a flake of graphene that is decorated with some potassium salt molecule that has been used for the exfoliation. So that decoration can be also seen within TM together with the size of the flakes. So in general, you will be able to answer to those questions here. So which is the shape and which are the dimensions, basically. Then you can start to use diffraction. And to start to use diffraction, you need to know which is the structure of the materials, actually. So this is the lattice of graphene. It's essentially formed by two intercalated hexagonal lattices. That is the honeycomb structure. So you have to use two lattices to describe it, because it is not a basic cell that is capable just to map this structure on 2D, on 2 dimension. And this is just the indicization of the index. And essentially, you can just see the colors here. So one is the atoms with red, and the other are the atoms that are depicted in blue. And this represents the two intercalated hexagonal lattices. And this first hexagon that is written here corresponds to a distance that is 2.13 angstrom. And the second one that is related to that spots here correspond to a distance that is 1.23 angstrom. Keep in mind that what you are measuring with diffraction in that case, or with this information, are not the interatomic distances, but the distance between the plane. And you have also to keep in mind that. So you are not just measuring that distance here, but you are just measuring exactly the distance between the different planes. And just to let you know, it also may happen that you will find a description that uses 3 index, just to mimic essentially the 3-dimensional structure that is not really the case of graphene, but just to have the same nomenclature available. And in the case of graphene, then you have a larger set of possible reflection, but some of them are not permitted. So these are essentially the rules. If you will find the 3 index notation to describe the spots, that means which are the planes inside your hexagonal crystal with this threefold symmetry. Essentially, this is the rules that is telling you which are the spots that are available. So the reflection, the planes that are really corresponding to your structure, and which are the ones that are not really available. So not permitted within the scattering. So that's just to tell you that you can find that nomenclature here, telling you which are all the planes. And you see that you have this plane here, the other plane on the other side, etc., etc. Or you can also find that description here, but it's definitely the same. And yeah, so this is what we are saying. And if you start from diffraction starts to tell you some additional information that you can just add to the description that you can achieve using just the imaging mode. So essentially shape and dimension. Then you can do diffraction on a flake. Here you see just a region with a selected area diffraction on a graphene flake. And this is the diffraction pattern that you can obtain. And this diffraction pattern starts to tell you which is the structure of the flakes that you are observing here. And if you look, for example, a little bit more in detail on that, you will see again that it's a flake. You are not able directly from the image to distinguish how many flakes or which is the structure here. But if you look at the diffraction pattern, you can immediately see that you have 3 sets of hexagons. So they are marked in blue, in green, and in yellow here. And essentially, this is telling you that you have 3 single crystals that are rotated one on top of the other. So there are a sort of turbostratic arrangement without any specific angle, actually. And starting from that, you can start to play with your instruments and just making a mask on top of it. So just selecting the first hexagons in yellow, for example, so masking the other reflection, you can reconstruct the image back, and you can obtain information on which is the region of the flakes that is giving rise to the yellow hexagon. So this is one crystal inside your sample. Then you can just select the blue spots only, go back to the reconstruction and obtain the region that is related to the second crystal, and then you can do the same with the green one. So this is a sort of artificial dark field. It's something that, like what Roberto was explaining yesterday, in terms of selecting a specific direction of scattering. Here, a specific direction of scattering, considering that you have a very thin sample, is just looking at which is the orientation of the crystal respect of the beam, and you can go back and start having information just from diffraction, combining diffraction and imaging on the grain orientation within your crystal. After that, you can try to analyze the thickness. And on that, we do not have any time to discuss this in detail, because you have to go down to the analytical description of how diffraction works. But just believe me, essentially, when you have, I mean, the intensity along Z of your diffracted beam, it's not uniform typically in a 3D structure. So you have a modulation in intensity depending on which size, at which level of set you keep your beam to form the diffraction pattern. But this is not happening for a 2D crystal, because, I mean, if you are just tilting your sample, I mean, along that, you will have always the same thickness that is traversed by your beam. If you have a thicker sample that is 3D, then the region that is interacted with the beam changes. So with essentially with a single layer crystal, you will have the same intensity of the, I mean, from the inner region compared to the outer region, even if you tilt your sample. That is not happening if you have, in principle, a three-dimensional structure, because this is the intensity that you should expect along Z of your diffracted beam. And if you have this intensity theoretically, and you start tilting the sample, and essentially what you have in your image is just the intersection between the plane of the sample and this intensity that is modulated along Z, means that you interact with this intensity in different points, and you have different intensities coming from the different diffracted beam. To translate this in practical stuff, you will see here, I mean, a single layer graphene, when this is tilt is 0 and that tilt is 10 degrees. And what you see is that essentially the diffraction pattern, so the intensity measurement along this line here, so comparing the intensity of the first hexagon and the intensity coming from the second hexagon, even tilting the sample shows you a higher intensity coming from the first diffracted beam to the second order diffraction. If you have more than one layer, actually, so that it's the case here, what you see is that is changing dramatically, because apparently you have the same structure. So you have always the two hexagon showing you that you are observing a perfect diffracted, a perfect single crystal graphene, but you will see that at the outer, the second order diffraction, when you start tilting the beam, becomes more intense than the inner one. So this is to my knowledge, the only way to say directly, without any doubt, if you have single layer graphene or multi-layer graphene. It's not giving you any chance to count the layer. It's something that you can do typically with Raman or with other techniques that we will see afterwards if you are lucky enough. But from a point of view to say, okay, I have only one layer graphene, this is the best way ever, because it's completely analytical, completely direct, actually. So this is what you can do also within your material. So this is, again, the real experimental image. You will have a flake over there that is just on the top of the carbon film supporting, and here you have another flake. And if you do the measurement that I was showing you before, you can directly achieve the information, the fact that this is a single layer, because this is the effects, I mean, that you have tilting the between 0 and 10 degrees. That is the same image I showed before. While, I mean, if you do the same measurements on the other flakes, you will end up being able to assess that in other regions you have more than one layer superimposed one on top of the other. Then you have to move one step forward if you would like to analyze graphene. So we had the information on the shape and the dimension from the imaging, information on the structure coming from diffraction. Then you have to move one step forward and move to the so-called high resolution image. So adding something to the imaging capabilities of your system. And this is a fundamental message that you have always keep in mind when you are dealing with high resolution TM. So high resolution TM is a phase contrast image. So it's a interference process to one extent. So it's completely forbidden, even this is slightly less stringent condition in two-dimensional materials, because you have one single layer of materials. But in general, keep in mind that it's always forbidden to link directly the intensity of the spots on your image with the position of the atom. So it's not an atomic map of the atomic position, actually. So in principle, it's completely depending on the focus and on the thickness of your sample. So essentially the type of the contrast that you may have, I mean, it can be completely different depending, just varying slightly the focus and the thickness. So you have no way to make a direct interpretation. Just to give you an example, so this is essentially the very schematic way how our resolution works. You have the incident electron wave, you have the sample, and you have all the transmitted beam along the different direction related to the ordered structure you have in your sample. What is essentially is doing your optical system is to bring all the waves scattering along the different direction and bring them superimposing in an interference pattern on the imaging plane. So, and this interference pattern that is in fact a phase contrast image is what you call high resolution image. So from a very principle, a very theoretical point of view, I mean, if you are able to identify, to distinguish any of the diffracted beam, it would have been simple just to go back and to have the direct image of your crystal, just theoretically. So because each diffracted wave represents a different solution of the Schrödinger equation, and I mean, everything is depending on the periodic potential you have in your lattice. So in theory, you should be able to go back to the real structure. But in fact, I mean, you have very poor lenses, as I already pointed out. So they are affected by aberration. Aberration, I mean, is just changing. They are not making, I mean, the focusing on the beam perfect in any point, just depending on a slight distance difference in distances from the optical axis. And then you have, I mean, the aberration that is there. This is changing the wave shift of each diffracted beam that in the end, it's a mess. What does it mean it's a mess? Here, you see just an example. See, this is the theoretical image of a silicon nitride materials that should be in principle the mapping of the structure. And this is the real, I mean, this is the real structure that you should expect, sorry. And this is the so-called scrambled image, means what you really see with your high resolution image. So this is the structure that you should expect in principle, and this is what you get, I mean, in real image. So without any capability to simulate the TM condition and the structure of your sample, there is no chance to start from that and to go back to the real structure. So if here you try to interpret this as a real map of what happens, or a real map of the atoms, you end up with something that is completely wrong. So the statement that you have to, I mean, to take as a take-home message actually is that the lattice image do not depict the projected atomic column. Instead, they are interference pattern of the direct transmitted beam with diffracted beam. The true column position of the projected crystal lattice may correspond to intensity maxima or minima, or any other value depending on the objective lens, focus, and sample thickness. So this is our parameter that with TM you have always to keep in mind, even if this is partially relaxed with the new instruments, with the aberration correction, and so on and so forth. So just see how we can compose a high resolution image. So you start with this, you saw already yesterday in the lecture of Roberto, a sort of picture similar to that one, but you have your optical axis, your beam that is coming through, your sample, and then your objective lens. And if you start thinking that you have a first set of planes, just one-dimensional ordered structure in your system, then you end up with a first interference pattern that correspond in the reciprocal space to one distance, so two spots that are corresponds to the distance between those planes. Then if you have to construct your three-dimensional structure, you can just to add a second set of planes in your theoretical structure, and your system is making only the superposition of this first of diffracted beam with the second set of diffracted beam, and you end up with something like that. And if you add a third ordered structure here, and you just sum up, I mean, the third ordered set of diffracted beam, you end up with an image like that. And this image like that appears exactly like a modulation of spots, black and white, that just recalling you in principle the crystalline structure, but is nothing that the superposition of the diffracted beam coming from the three different planes. And within that, even if you have some small deviation of the plane, some rearrangement on disordered region here, will reflect in a modulation of intensity or interference pattern. That is something that will be recovered afterwards, just describing what can be done with graphene. So just move to the real sample. So here you see again an image just recalling you only the morphology. It's a crumpled crystal of graphene on your grid. But I mean, if you look at the region 1 and then the region here, the region that is number 2, that is that one, you see that here you have your structure that is folding over itself. And that line that you see here is just like taking one sheet of paper and folding it over itself and looking from the top. So if you have to look at that folded region from the top, if you have just one single sheet of paper, you will see just one single line. That is just the stacking. But if you have 6 layers, so just 6 sheets of paper folded over themselves and looking from the top exactly on the border, you will see these lines here. And these lines here, nothing that the stacking along the 6 layers of graphene, that here in this region where you see that it is thicker, you can just count. And with that, as we said, if you are lucky enough to have some folded region within your sample, you are able to direct measure the number of layers, just counting that part here, because this is nothing than a high resolution image seeing the ordered structure in Z of a few layer graphene. So 6 layers of graphene here folded over themselves, you can just count, and this distance is about the 0.34 angstrom, that are the 3.4 angstrom, that is the distance along the stacking. So this is an enlarged image of what I was saying, and here you see exactly the high resolution image showing you the 6 layers folded over themselves. And so if you add to the information that we had before the high resolution capability, then you can answer to another question, that is which is to determine the atomic structure of your system. Here you see a high resolution image of a large crystal size of graphene, and again you combine the high resolution capability with diffraction, and with diffraction you can see that here you have 4 hexagons, and with this 4 hexagons you can say that here you have the superposition of 4 different layers, one on top of the other. And here is an enlarged view. So here you have the high resolution with all the atomic structure depicted, and here you have the layer. In this case, there are 8 layers of graphene or superimposed that you are looking exactly on the top of here, and you are just measuring this distance here. So you have also the capability to resolve clearly, I mean, to count the layers, so to have a precise determination of the thickness. Okay. This is another example that you start from morphology. There are some residuals of the transfer here, just the structure, but also you can go up with the magnification, with the resolution, and you can, in the high resolution image, you can just see that here you have a single layer film that is not capable to be understood clearly from here, just counting the layer that is here. That you can push more with the resolution, with the capability of your instruments, and you can achieve with better images than the one I was showing you before. This is a high resolution TEM bright field. When you really see the structure here of the single layer, the point is that that distance, if you keep in mind, I mean, the dimension that we were talking about before, so that the minimum distance is about 1.23 angstrom, needs for instruments like the one that also Roberto was showing yesterday, so the instruments of 200 kV, needs to add the so-called aberration correction that are pushing the resolution down to sub-angstrom regime. And in that case, you can just clearly resolve completely the ordered structure within your sample. And also you can do it with the so-called STEM. STEM means scanning transmission electron microscopy. It's essentially the modality to work in the TM, just putting together the CM characteristics, so the beam that is just impinging on one point stays there for a certain amount of time, generating a series of signal and modulate the intensity on the screen. As we said, there is also the point that you typically can generate some artifacts or some superstructure that are superlattices that are just related to the superposition of different layers. So previously we saw the region where you have different layers stacked over themselves. If you just look to diffraction, you can just see the different orientation of the crystal due to the rotation of the diffraction pattern. But if you look at the imaging, then you end up with structure like that are just related to the fact that you take an hexagonal lattice, you put a second hexagonal lattice on the top, and you start rotating at the certain specific angles. You will see clearly that some superlattices, superstructure are formed that are called Moiré patterns. And you can see that here you have an additional structure, for example, that is that one, that is not really related to the real structure because it's not related to the structure of the two crystals that are superimposed, but just related to how they are seen when the two ordered structures are superimposed. And you can see clearly here that are several superlattices are forming just depending on the angles. And again, keep in mind that point here, because sometimes it may happen that you see some specific structure within your sample that are not real structures that belongs to the crystal, but just related to the superposition. What is helping you is typically the size, so that the distances of the superlattices that are forming here are much bigger than the real crystal structure, so it might be not so complicated to isolate. This is not just an artifact, I would say, because this is just a spot. But if you know, I mean, between 2018 and 2020, it has been realized and discovered that a control of the moiré, so a control of the rotation among the layers, may also have a huge effects on the transport properties of graphene. So here you see that just changing a little bit the orientation causes a complete rearrangement of the bands, and there are some specific angles when you can just turn the graphene from insulator to superconductor and so on and so forth. And that magic angle has been identified around, I mean, very, very few degrees, and it has been kept studying also in the following years. Okay, then I mean, you can just use TM to move forward in the characterization of the materials in order to get additional information. So if the resolution of your system is good enough, you can also move not only to the definition of the thickness or whatever, but also to an atomic sensitivity level in order to really see what happens at the atomic level on your structure. So here you see a single layer graphene, and here you see some contaminants on the top. You can directly reconstruct the structure when the crystal is perfect, but you can also see where there are present some specific atomic contaminants on the top, or as we will see in the following, we have some dangling bond or some defects. So you can push, I mean, the level of information at the real atomic level. So here you see the stacking. So there are more or less the same characteristic I was showing before. So the stacking of two different layers. But here you see that if the resolution is good enough, just having not only the stacking in Z, so the folded part of the layer, but also the capability to have a direct observation of the atoms, you can discriminate between the different level of stacking. So here the so-called AA or AB stacking means that you have your hexagonal lattice, and AA means that the second lattice has the atoms exactly superimposed on the initial one. If you have the AB, you have a half cell shift, so you have the second atoms that is essentially at the center of the hexagon of the initial one, and this is something that can be seen here. You have a perfect alignment of the atoms, and in that region here, for example, and while here you see that you have a shift of alpha atoms somehow, and you have the AB stacking. Within that, you can also follow some process within your materials, just seeing what happens when you're observing. Because I mean, Roberto was telling you yesterday that the TM is a destructive technique, but for, I mean, beam sensitive materials is even more destructive, because I mean, you're not only destructing the real samples, means that you have to observe very in small region, but you have also in the region when you are damaging directly your sample. That is another point that you have always keep in mind when you're working with TM. So this is just following the process within a graphene flake, just in something like 5 minutes. And you see that you start destroying, here you start just removing atoms from the contaminants on the top up to drilling holes within your samples. Because I mean, you can, this is essentially the reaction that are happening on the top. And the source of damage in this case is just the so-called knock-on. Oh, okay. Means that the electrons of the beam have enough energy that can kick out the atoms from the lattice. So you just remove atom by atom just interacting with your beam. And the threshold, I mean, the calculation that you find theoretically are based on graphite, but essentially the threshold is below 100 kV. So with beams that are energy higher than 100 kV, this happens very fast. If you go down with energy, you can, I mean, keep a little bit more control on that. And this led us to, I mean, the present generation of instruments, the high-end instruments, I would say, that has been essentially pioneered by this so-called Salve project. It was a project that was carried out in Germany mainly, developing instruments that are working at very, very low energy. So here you see a couple of examples, I mean, because here you see the threshold energy essentially for materials with low atomic number or low dimension, and you see that threshold energy goes down. I mean, in particular, if you have a very materials made with very, very light elements. So it means that you have heavy elements, you can also use high energy, but if you would like to work with materials having a low atomic number, then it's mandatory to work with low energy. But low energy means that you have a terrible resolution within your instruments, and the only way to keep the resolution good enough is to push all the part with the new instruments with aberration correctors. And that was exactly the idea, to develop TM that are capable to work at very low energy. So you see TM images taken of molybdenum disulfide or graphene at 30 kV. And this is the so-called also gentle stem. So here you see an example of some images taken at 60 kV of graphene, and you see that you see perfectly the hexagon structure here, but you are also capable to see where you have an atomic contaminant on the top, because the intensity is here, so you have some additional atoms here, or you have dangling bond, or you have folded edges, and so on and so forth. And you are not destroying your sample because you are working with enough low energy. Let me just skip a couple of examples here and go down to the last example I would like to show you. So we are going back to something that is similar, that is also holography, but more in general electromagnetic interferomagnetic techniques that are another capability that you have within your TM. As I already said yesterday, in principle, when you acquire a TM image, it's just a purely intensity, because you have the square modulus of the wavefront. Means that you are losing, in principle, any information about the phase. So a way to recover the phase, as shown yesterday, could be holography. So means adopting a technique that is capable just making the interference between a diffracted beam and a beam that has not interacted with the sample and the beam that has interacted with the sample, and making the interference of these two different beams in order to recover terms that keep the information about the phase. But in general, from all those techniques that are dealing with phase, you can obtain a lot of additional information that are not always available within the pure imaging modes. And in general, these are magnetic and electric fields, crystalline potential, but also geometric displacement. That's what Roberto was showing yesterday. So if you can just avoid, consider that you don't have electrical magnetic additional field that can be measured, then you can just focus on that and measure potential and strains within your materials. And yes, there have been already discussed the measuring of strain, but strain can be also apparent to some extent. So if you just use the same technique that we shown yesterday, that means geometric phase analysis, that we will choke slightly in the next slides, and you just take one of your graphene layers, like that one, and you consider that this graphene may be not completely flat. That is what happens when you have a folded edge like that one. So this is exactly the structure that we are observing before. You have to consider that when you are looking from the top, because imagine that in TM you are always projecting the image on the three-dimensional image on a two-dimensional plane. A folded layer of single atoms that is folding in that way will appear in your image in that way here. And that projection here, it's definitely something that appears like a strained crystal. So here you have a reduced distances between the atoms that is not real, but is related to the fact that this is just a projection. So this is what happens when you're observing a folded edge of graphene. And this is, I mean, this is just a single atomic chain. This might be the single layer graphene banded somehow. So they will appear compressed. So in principle, the modulation of intensity with your high resolution image, as shown yesterday by Roberto, can be used not only to determine the real strain, if there is no real strain, but can also be determined which is the three-dimensional structure of this structure here. And this is what has been done in a real graphene layers, actually. So this is the folded chiral membrane that we already saw. And geometric phase analysis means that you take the high resolution image here, and then you do the Fourier transform of that, and you just analyze, as shown yesterday, the modulation of intensity within the two different directions of scattering. That means that if there are some variation of intensity, if you recover what I was showing you in the previous slides, when we are forming the high resolution image, some small changes of the structure, the projected structure, may give rise to some different modulation of the interference fringes. So just analyzing these two stuff here allows you to recover the apparent phase that is called geometric because it's related to the modulation of intensity of the real structure. And you end up with a map like that, that is just telling you that is an intensity map of the apparent strain. And with that stuff here, you can just calibrate that map that is coming from geometric phase analysis that is written here. And you can just recover that measuring exactly which is this distance here and which is the slope. So the angle that the three-dimensional structure is forming. So just starting from the high resolution image, I mean, and combining with this geometric phase analysis, if you can easily, in principle, separate the fact that that kind of strain, here you see that you should expect a strain that is around some percent that is definitely too high to be a real strain in your material, because with this strain, the material will be completely broken. Then you can say that that apparent strain is not a real strain. You can relate this strain just to the fact that the material it's not flat. And you can use just a simple, let me say, imaging mode in order to reconstruct the three-dimensional structure. On the other side, you can deal with the real phase, and we will stop with that. So going back to holography. So holography means that this is the classical image, just the intensity, you lose completely the phase term, or you have the superposition of the real image of the beam that is interacting with your samples and a second in phase wavefront that has no interaction with the samples. And the intensity that you obtain with this interference pattern is written here, and you see that basically you keep a term that is directly related to the phase term. If you are able to just reconstruct what you obtain and just to isolate this term, that is something that can be done with some software and so on. 1 minute of it. Then you can just recover the information on the phase. So just to conclude, what you can do, I mean, you can do holography just having an electrical wire at a certain potential that is just divide the beam and allows you to have a beam that is not interacted with the samples and the beam interacted with the samples, and you can just measure the fringes that you obtain. And those fringes, if there are no additional fields, are related to how the so-called projected potential. So how the structure of the samples is just projection. I mean, the interaction, the interaction of the valence charge within your materials. And this is again what you can do. So you can take the same samples that I shown before. This is a phase map obtained in lithography, and with that, combining the three-dimensional structure, what you can achieve is then you can see essentially when, I mean, the potential is changing along the folded region, and you can just assess that when the layers are at the certain distances, you can consider them, even if this is a two-dimensional, it's a two-layer materials, completely decoupled, and they are acting as single layer. So here the contribution, it's independent, they are coming in just from, I mean, the two layers independently. Here you see the effects of the coupling of the two layers that is giving a different signal. And that's maybe important because, I mean, as we also heard this morning, I mean, strain, it's important also to sometimes to tune the properties. And in this way, you can see where, I mean, the deformation of the structure is giving you to a coupled structure or the completely decoupled structure. Okay, I will stop here.
Any questions?
Any questions?
Yeah. Can you come here so we can hear you?
Is it possible to is it also possible to observe diffusion of defects by using TEM?
Pardon?
Is it also possible to observe diffusion of lattice defects by using TEM?
Yeah, you can do it. I mean, there are some. I mean, it's similar to the what I was showing you. Is following this. I mean, progressive destruction of the structure. So you can just observe the materials and see during the observation what happens. You can also. I mean, there is no time to discuss today, but there are also the option to induce some specific stimuli in order to control the evolution of the defects. Let's call it with some in situ approach, and with the new instruments capable to acquire a large set of data, you can see the different series of images showing how the defects are moving or are changing based also on the external stimuli.
So you can extract, for instance, diffusion lengths and energy barriers could be extracted as well. How many?
Okay, energy barriers depends. Yeah, so in terms of diffusion lengths, to see how the defects are moving, I think that can be easily done. Energy barriers depends on the need them into some modeling of the materials, because something that you cannot really extract directly from the images actually.
Okay.
Any other question? No. Thank you. So let's welcome Ennio. Okay.
Ne ho due, questa è la prima e l'altra qua.
Due chiavette o due presentazioni?
Esatto, perché era piena.
Ah, ok.
La legge di Murphy.
No.
Si chiama Ari qualche cosa. Esattamente.
Non è ancora l'autorizzazione. Dai.
Che buttare via brutalmente. E l'altra si chiama MCC.
Ok. Questa?
Sì. Grazie.
Sì, aspettate, l'apro. Con quale vuoi iniziare?
Ari.
Ok.
Grazie. L'oggetto funziona.
Sì, ma si cambiano le slide qua.
Ah, ok.
Ok. So let's welcome Dr. Ennio Capria.
Thank you very much. Hello, everybody. Well, I think I will stay here, though normally I jump everywhere, but it's more adapted for a school. There is a proper station here. So thank you very much for the invitation to the organizers. I'm Ennio Capri, I'm Deputy Head of Business Development at the SRF, the European Synchrotron, which is just a few hundred meters down in the quasi island of Grenoble. So I kind of got a freebie from the organizers. They more or less told me that they were looking for a presentation or an introduction to something that was a bit more into the strategy at policy level, and also maybe with the point of view of the analytical research infrastructure of what's happening in characterization, and in particular with an eye toward the industrial needs, which is more or less my sphere of competence and my sphere of activity. So today I'm going to have two short presentations. Don't be scared. The first one is about the use of analytical research infrastructure to support industrial innovation. And first of all, my background, I'm Italian from Torino. I had my basically all my career based on nanotechnology. I went into characterization a bit after starting making materials and realizes that in order to make good materials, you need to characterize them very well. And I ended up at the end of, in the last part of my career with the research infrastructure when I fall in love with synchrotrons. So that's more or less my background. So here, when I'm going to tell you about these aspects, so I'm going to focus more on what we say beyond the lab or complementary to the lab. So probably all the challenge project and everything you are more familiar is with instrument that you normally put on a bench and you use it for characterizing your material and doing fantastic things. My job is the other way around. Normally the instrument is bigger than you, so you enter in the instrument is a facility that is a ring 1 kilometer of circumference, where basically you have 40 beamlines working in parallel, and where we generate very brilliant X-rays to characterize the samples. And normally these kind of instruments are run in a facility mode, so you go there with your sample and you measure it, and you walk away with your data. So it's very much a different kind of approach with respect to an instrument that you have in the lab and you can use whenever you want. And the idea is very much that you do everything you need in the lab. When the lab is not far enough, you use these facilities in order either to get your benchmarks and develop your metrologies, or in some cases you really need to use the synchrotron or the neutron, all this analytical research infrastructure very much for doing what you need, because there's no other way, like for example in the drug discovery for protein crystallography and things like this. So let's go now to the use of analytical research infrastructure to support industrial innovation. First of all, what is technically an analytical research infrastructure? Is basically a combination of tool, technology, resources, and methodology, and also a collection of processing, analysis, and interpretation of data. Okay, so it's not just a physical thing. There exists also distributed research infrastructure. So you have to think about it's very much the fact of having a dedicated tool that is making it being an infrastructure, analytical, because normally we offer investigation of materials and device, and we based on their physical and chemical properties. And also, and for sure, we are designed, and our mission is to facilitate rigorous and systematic investigation. And the idea is very much to create an environment and not only to offer a punctual characterization in order to produce robust and reproducible analysis. So the keywords are very much infrastructure, which is the difference between this kind of facilities and other kind of things, and analytical, because we are going to look into physical and chemical characterization properties. The first point that I wanted to raise is the fact that analytical research infrastructure in Europe are coordinated. There is a very nice network of networks called ARIE, where basically you can see photons, electrons, lasers, ions, protons, high magnetic field, and neutrons that are organized in order to answer collectively to some I'd say European social and technological challenges. So that's the first point. There exists a coordination. So I would like to invite you very much to have a look, because when you go to this site, basically you know you can kind of have a complete overview of everything is happening around Europe. You can see 110 facilities are represented there. And here you can see also on this website a couple of publications. One is on basically what this infrastructure can do for European challenges and opportunities, and in particular how this research infrastructure can answer and can address Horizon Europe mission. So this is very much designed for people thinking about designing new programs at policy level or new projects at basically exploitation level. Now, what is unique with analytical research infrastructure, of course, is the fact that you can have unique data and methods at the multi-scale, addressing from the atomic to the crystalline to the material and the final object scale. And in particular, when you are at atomic scale, you address physical-chemical properties. No way to go and see atoms or things like this, though people says are super microscopes or things like this. We just can have some, let's say, basic material information on physical chemical properties. Then on the crystalline side, we can go and sound the microstructure. So something that is very familiar for you is the residual strain. Indeed, there is a huge activity, in particular with synchrotron in the reciprocal space mapping, with the spatial localization and all these methods that are useful for where you can basically identify tilt and strain, and also some delta in your thickness of your epitaxial layer. And of course, phase recognition. And then at material level, we can address morphology and up to the final object. And we say that you go beyond the lab. Why? Because normally you're going to have either a higher penetration depth or a higher spatial resolution on a higher, time resolution and higher detection level. And of course, everything can be operated in situ under real operating condition and multi-scale. So this is very much to tell you, think laboratory. When at the laboratory, you're limited by something that is looks like capability to go and see inside, or some, let's say, some resolution in terms of space and time. This is the time to go and see the ARIA website and see maybe there is something around there that I can go out of my website. This is basically the focus of my point. And these are basically all the sector that we can address, which is making, now I make a bit of the publicity for the new generation of science. What is very nice of going and work in a facility like this is that more or less every day you can do stuff that is related with a few of those fields. So if you like applications that are very diverse, it's a very nice place to work. And of course, when we talk about industry, you can see here we have a subset of our clients. So it's very much generalized. These guys are clients that accepted to communicate because, of course, everything we do is supposed to be top secret because it's with industry. Now, if these are in general research infrastructures and what we do. Now I'm going to focus a bit more on the contribution of research infrastructure to industrial innovation. Why? Because very often people think that we are kind of very much into fundamental science, very difficult to access. So in reality, when we are talking about applied science, people think that maybe this is not the right place to go. And I wanted to show you that this is not true and that we are actually doing something. We're very committed into doing something in this sense. And in order to do this, I started to consider all the different steps that goes in basically in what is the so-called new product development. Okay, when you start from developing an idea, validate your idea, build a prototype, then you go into the marketing side, you create the messaging, you build the product, you release the product, and you improve the product. These are basically all the 7 steps that are more or less recognized as the product development chain. In each one of those steps, you can consider that you have at least 2 different phases. The first one is the so-called pre-competitive phase, up to level 4, and the second is the confidential phase. So first thing that we can demystify is the fact that when we talk about industry, everything should be confidential. So as you can see, probably most of the industrial activity is in the pre-competitive phase, which is not at all confidential, and is, of course, for publication. And so in which way our facilities can help in this different phase? For what is about developing the idea, validating the idea, academic access for publication. Normally, industry, either in collaboration with academia or alone, come to our facility, and they access and with the willingness to publish some results. Then we start a second phase, which is a bit more delicate and where European grants like challenges are playing a crucial role, is when you go in this long-term collaborative approach, which is basically catalyzed by grant. And then we go into the confidential access for everything which is entering the confidential phase. And in this one, we can provide this confidential access. So we have agreement with companies on in writing NDAs and etc. So as you can see, working with industry in a large-scale facility is not only selling beam time. Selling beam time is just one of the last parts. And we sell beam time not because we look for the money, but we sell beam time because it's the tool that allows us to give to the industry what they want in terms of confidentiality. Otherwise, on our side, what we're very much interested is to the impact that is exactly addressing each one of those points in each phase of this. And then when we go into a even further level, here you can consider basically which kind of phases we address in this new product development. Where we are in the first four steps, we are basically in the set of process and product design and optimization. So we're very much in the R&D phases. When we go on the orange phase, which is more in the, let's say, in the phase of where the product is built and is going to be released, then we move into another dimension, which is more related with standardization of the process and having statistical results, a lot of results. So as you can see, these are 2 different kinds of jobs. First part is unique, maybe complex experiment, tailored to the need of the customer. On the orange phase, we are very much into, we just have to do a lot of sample as fast as possible, very standardized, and possibly even not very expensive. Okay, and this is something that should, in a way, be reflected in our way of working and functioning. And there is an extra bit one that is in the blue phase, which is the benchmark. We don't have to forget that most of the contributions that are coming from the research infrastructure are for giving benchmark results. And then people are developing their own metrology in the lab, and they do their stuff in the lab, and it's in the lab that all the things happen. But we're there just in the support. And so if I convince you that these blue and orange phases are different, you can see what is in the blue box and what is in the orange box. On my point of view, on my perspective, in the blue box, I'm going to put this ad hoc, in situ, operando, low number of samples. And all what I'm putting in the orange one is routine service, mainly ex situ, a large number of samples. So if you look it in a kind of Manichaean way, going from up to down, the complexity is reducing, and going up, and in the other way, the standardization is increasing. So basically, standardization is taking the place of complexity. So this is our job at the facility, and we have to interpret it in the right way. Of course, if this is what is needed by industry, if this is what we are supposed to bring, and what our challenge is to bring, we cannot avoid considering that there are certain barriers between industries and analytical research infrastructure. I'm not going to talk about this. I had a talk dedicated to this topic 2 years ago, another impression. and probably I can share the presentation with some of you if you are interested. But I just mentioned one, which I think is the most important, is the translational. Basically, this is how we see ourselves. We are a unique, large-scale instrument, state-of-the-art, that does fantastic science. This is how industry sees us. Expensive and difficult to use, risky, fundamental science, not for me. So that's the barrier we have to win. So all the stuff that I show you here is we are very much engaged in doing this. We realize what has to be done. We realize the complexity of the job, but this is the starting point. Okay. And this means that it's not just a question of translation, though I call it translational, but it's also a question of lack of experiment design, data analysis, and etc. So we need very much of dedicated resources that sometimes are outside our DNA, if you want, of our mission. And this is the reason why more and more we start to work in collaboration with the so-called technical infrastructures, who are centers like the CA, for example, where that are very much at the interface between academia and the research infrastructure. In this case, we can do what we know how to do, and we have these centers of expertise and excellence that can help us dealing with all the parts related to experiment design, data analysis, and etc., which are a bit more difficult for us. So if you want, you can have a look to this project, RITIFI, which is pretty much interesting because it's the first attempt of the Commission to produce something a bit more formalized in this new way of having this relationship between RI, TIs, and industry. So, if I go a step back in the following of my thinking, I show you that what we do. I show you that this is important for industry, that we have these two dimensions, the blue box, the orange box, you remember. If you think about this, we can imagine that at the research infrastructure, our job could also be to build new services, not only giving open instrument to industry, but building new services. And if you think about this, this is not something that you can improvise. Here, for example, I show you something that I'm trying, this is a concept that we are trying to, in a way, conceptualize a bit recently, where basically you have on the horizontal axis the so-called TRL, technological readiness level, which is something that everybody knows. It's the way that the technology is advancing. You start with an idea, prototype, validation, valorization. In blue, I put normally the 3 instruments that are available in the EIC, because when I showed this thing, I was in the EIC. But what is very important on the other side are the MRL, the marketing readiness level, which very often we don't consider at all. We think that there is the TRL, everybody concentrate on the TRL, and then somehow we will go to the market. Now, if I show you this blue line is exactly for a service generated and developed into a synchrotron, how a certain TRL corresponds to a certain MRL. As you can see, we are constantly in the low lower part of the chart, which means that we are constantly in the tech push approach. We're constantly into this situation where we have to develop something before the market is asking for this something. Until the TRL 8, where then we basically have the method that is adopted by the market drag everything, and then you go up and you start having different synchrotron that are developing the same thing. You enter into the competitive phase, and basically your service became a commodity. This is not obvious. This is just for synchrotron, because in other markets, for example, I don't know, the telephones, probably you're more into the MRL side, because people want to have a certain telephone with certain characteristics, and the technology was not even able to bring. Probably you desired your iPhone before that Apple could make one. It's not the case, unfortunately, for the service at the synchrotron. So we normally have to demonstrate that something is doable, show it to industry before they start to desire it. And so in this respect, this is very much the work that has to be done. Each one of these MRL, I didn't go in details, but basically is a certain set of steps that has to be done on the market, internally and externally. What does it mean internally? It means that sometimes, at some point, you cannot take the risk that you develop your things too fast, and then you have too many clients, and your team and your basically your people internally that doesn't want to do what you want to do, because they say this is not my job, and then you're stuck. Okay, so in the MRL side, you don't have also only to think about business development or marketing, but also about the team structuring properly the, let's say, the moral of your people doing the work. And of course, also in that sense, you have the ideation, the testing, the introduction to the market, and then the growth. What the last thing I wanted to say is that what is very important is that when you want to establish a new service and you want to follow this blue path, that is the ideal path, you cannot only think about engineers. More in particular, here are the scientists that work. From here on, we start deploying engineers, and maybe here more technicians. But for this axis, we need business developer and marketing people, also on a synchrotron. Otherwise, we stay here and we basically develop something that is a solution to no one's problem. Okay? And all this part of the MRL today is extremely, let's say, badly addressed, and people improvise. There is not a formalization. And this formalization needs to be done, and this is something that we are working on. And yeah, I was also trying to put which grants can correspond to which phase. And as you can see, clearly we are we move from the pillar 1 to the pillar 2 to the private funding when the money are there. So when the euro signs start to show up, the private funding arrive. Unfortunately, private funding don't arrive if the euro funding is not already there. And here I can show you, for example, the project Easy Stress I'm involved in. It's one of this NMBP 35 project. This is exactly what happened. We started the project when we were in this situation, TRL4, MRL2. Thanks to the project, we could climb to TRL6 and MRL4, but now we need to find a way to arrive to the TRL8 if we can. And this, you can see that this scheme is also very practical when you want to demonstrate, to show to someone what you want to do. Basically, okay, I have a service, I'm here, I want to do it there. So in conclusion, I hope that I convince you that analytical research infrastructure can support industrial innovation, and that industry has different needs. So it's not true that doesn't exist such a thing called industry, but only industries, each one with his own specificity. And of course, it's important to address each level of the new development cycle in the proper way. I spoke about barriers and the ways that technological infrastructure can help us to overcome the barriers, and also funded grants. And in particular, one thing that I didn't talk is about the synergies between Pillar 1 and Pillar 2 actions. Today, these are very siloed in Europe. So basically, either you have a grant for doing Pillar 1 actions, and then you take the money and that's stop, or a grant for doing Pillar 2 action, more industrial. But the problem is that when you intercept an industry with your grant in Pillar 2, maybe this industry needs something that is more fundamental. So you can go and knock at the door of your colleague that are maybe running an action more fundamental, instead of saying to the people, no, this is not for me. And this is something that doesn't happen today. I give you an example. We work on a project called NFFA pilot, is dedicated to nanotechnology. We give free access for a fundamental problem and people that can do a publication. In Nanome Commons, we develop some workflows for the nanotechnology. Of course, what we do in Nanome Commons is much more applied than what we do in NFFA. But sometimes some of our industrial come with problems that are pre-competitive. So doesn't have the aim to address it in Nanome Commons. So we could go to NFFA and say, look, hey, I have this client for you. Just help him, make him climbing to the level of when the pre-competitive is finished, and then you take it back on a Pillar 2 action. So this kind of actions should be in a way transversal. And because industry doesn't have always problems that are doesn't have always problems that are in this phase. This we have to be flexible and address everything at the right level. Okay, so I finish with this part. Questions? Okay, if you don't have any questions, I go to the second part. Okay, so basically the talk before was very much about ESRF, research infrastructure, and the ESRF in particular. That is what we do on the other side of Grenoble. This part is going to be dedicated more to an initiative, which is the European Material Characterization Council. Upon request of the organizers, I decided to give you this introduction, since I'm one of the members of the organization management board. I don't know for how long, because I hope that we're going soon to have a general assembly with all the members of with all our associates, and maybe we're going to nominate a new OMB, and that will be something very, very nice. But for now, this is the situation. So I will be happy to tell to you about the MCC. And the reason why I'm in the MCC is very much to bring the voice of the research infrastructures into this community, because I think we have some specificities that needs to be addressed. So you can recognize very well the tetrahedron of characterization that we have seen a lot of time, where basically characterization is basically the most fundamental things among modeling, data science, and manufacturing, just in between. So we all know that is important. This is very much the design you have to show to policymakers to say that it's important. And so today I'm going to tell you something about the history of the MCC, what we do in particular, particularly about the CAD activity, and the future challenges of the MCC. So with respect to the history of the MCC, here you can see the member of the OMB. You have to consider this organization a bit like an organization that organizes a conference. You normally have a management board that is there to make things working, but you don't have to imagine these guys as the most competent of the world on everything. No, the idea of the OMB is very much to build a set of people that believe into a project, into a vision, and try to bring it forward. And then we build this project with all the experts that we are going to call every time that we have a certain action, and etc. So this is the scope. the OMB was the same since quite a long time. That's why at this point we would like very much to. It's the moment to be more inclusive and opening. But since there was COVID, and then with the Commission, we didn't know very well what they wanted to do, etc. There was a bit of, let's say, waiting time. But if something is going to happen with the MCC after, is going to happen with this opening toward the community of the people that are our associates. And so, in the mission, the first statement is that is a bottom-up activity. Okay, it's not the Commission who decided to put in place a body that was making something, but more about the community that was trying to lobbying into the European Commission and the importance of characterization. Because for us it's obvious, but sometimes when you go at eye level, there's people that even start thinking about, oh, but characterization, do we care? And at some point someone asked this question, and there was a first survey that was run. This was in 2015, and basically with a very high percentage, all the experts of the sector of material, advanced materials, said yes, that was important. And then this was the idea of building this EMCC. So being also the expression of the community of European stakeholders for advanced material characterization. And in terms of specific goals, there is, of course, a goal related with common languages. I mean, and all this part of that is very present today, related to developing some common vocabularies, but also about the fact of having some interoperable platforms. So enhance the interoperability between different instruments. So common language doesn't mean just that we know how to call a certain element in our experimental chain, but also the fact that we are using instruments that are interoperable among themselves. And so the second point is very much about nanometrology and in situ monitoring, and how this will relate to industrial needs. And this is not a straightforward topic. And then, of course, provide a sustainable background for the regulation in nanosafety. Nanosafety is always coming in this point. And then support policy development, which is one of the most important points. And in terms of vision, of course, there is building a community around open innovation environment and open innovation testbed. I'm pretty sure that you know those two families of platforms that are basically one of the main outcome of of the first roadmap of the MCC. And in this moment, there is an important discussion related with the digital passport for the materials. And finally, bringing together characterization, modeling, data science, and manufacturing, which is one of the biggest demands and requests from the European Commission. And when we think about the stakeholders, of course, material scientists. This is clear from all the disciplines that you for sure know about characterization of material, but also developer and manufacturer of analytical instruments. So the vendors basically are an important stakeholder. Then material manufacturer and integrators, and of course standardization bodies. So you can see very much all the family here, going from the science to industry, to the standardization body, in case the policymaker. And so based on this, we developed inside the MCC different working groups, one in instrumentation and metrology, one in standardization, one on characterization and data management and information management, one on industry needs, and one on policy networking activity and dissemination, international cooperation. So if you are interested, you can always go on the MCC website, apply for becoming members. There will be, of course, an application to do. And when you're going to become a member, normally you're going to ask to participate in one of the working group. So one of the biggest outcome of the MCC was the roadmap in 2017, which was not an obvious exercise to coordinate, and you can see that out of one of the biggest outcome of the roadmap are all those calls that has been somehow defined following the recommendation of the roadmap, that are for open innovation testbed, open innovation environment, and all the harmonization call and the call related with the workflow, let's say, or interoperability. Interoperable platform, such as, and then you can see, you probably recognize some. I'm, for example, myself involved with Easy Stress and Nanome Commons, and TSMAT as well. There was an open innovation testbed, and maybe some of you can recognize themselves. Add more power as well. Yeah. So if this is here, I forgot that there was this this slide. This is even more obvious. You see, you start with the open innovation platform, which is the level, the smaller scale interoperability set. When you go to testbed, are a bit larger. Then you have the real-time advanced characterization, the harmonization, and then integration between modeling and characterization, and then modeling, characterization, adaptivity. It is very much answering the objective that I gave you before, where the final one was about the joining of modeling and characterization. Okay. And one of the main action that we are running today is very much about the CADA activity. I'm not going very much in detail, but the EMCC developed CWA. It is a kind of a CENELEC, is basically a standardization a norm of the CENELEC. And this norm was basically defined in order to establish these CADA. That is a set of recommendations that can help you to describe in a kind of universal manner any kind of experiment, and use a set of metadata indicators that are going then to be the settlement of your data management protocol or process. Okay, so the idea was very much to try to develop a rationale that could describe any kind of experiment, and out of this a set of universal somehow descriptors of the experiment. And in this way, the ambition was to create something that was very much interoperable among different instruments in a workflow or different workflows. Each one of the projects that you have seen before, I go back again here, somehow has been asked by the Commission and has a work package where they are expected to generate a CADA with the data that they are, with the method that they have developed. And in the project where I'm involved, we all did our own CADA. Now, one of the activity of the MCC in this moment is that all these CADA are kind of drafted as either a deliverable or an Excel file. There is not something, a tool, let's say an informatic tool that can help us in collect everything in the same place and in a way that is easy to search. So the next step will be probably into this this instrument to make this opportunity available in a larger way. Sorry, I go back. So, and here you can see basically on the how the basic experiment is described. Then, of course, we are going to have other adapting of this concept when you have, for example, some experiments that are the so-called multimodal or where you have workflows, so different sets of chain of experiment in series or in parallel, and then you can complicate the thing as much as you want. Future challenges for the MCC is basically the new roadmap. I would say that this is an idea that is on the table, but will probably be discussed with the associate and will be with the next initiative of the next OMB in case this will happen. But in order to anticipate this, we launched a survey. So the MCC 2023 that is still ongoing. So will be normally we measure, will take more or less 16 minutes for you to fill this in. And so if you are if you feel so, just scan this QR code or go to the MCC website and fill in this this survey. Is we already had a certain number of answers, but we are not publishing the results before we feel that we have let's say yeah, a reasonable sampling of the population around. And this survey addressed very much all the aspects of characterization, not only technical, but also related with, for example, in situ or operando. Is this important? Is not? Or also all the part related with the digitalization and interoperability and harmonization and all this this part, including the new digital passport and etc. And I think with this, I finished. And yeah, if you have any question, otherwise, thank you.
Questions? No?
Oh, was not very complex and quite diluted, so I can understand. But feel free to make the survey. This is the most important.
So thank you, everyone. Thank you to all the speakers that were here and to all the participants who attended the second Challenges Training School. The training school has officially concluded. So thank you, everyone, again for participating. And if you have any questions, you have all our contacts. Thank you.